Hello and welcome to Red Team Operator Malware Development Intermediate course. My name is Renzo and I'll be your instructor in this course. This course is a continuation of Malware Development Essentials, but it's not mandatory to take it before this one. If you know the basics about PE files, string obfuscation, code encryption, classic process code injection, and how to program and compile C applications, you're good, all right? Otherwise, I recommend to check Essentials course first. So in next few hours, we will cover more advanced techniques. We will start with discussing PE file format in detail because we want to implement a custom variation of GetProcAddress and GetModuleHandle functions. And this will take us to creating a PE binary without any imports. We will also talk about variations of code injection, but this topic is huge and probably we could spend the rest of the time to discuss only code injection because there are so many different flavors of this tactic. So we will focus on about 5 of them, all right? Then another big one is ReflectiveLoader and how to create reflective DLLs, both from source code and from binary only. We need to cover Windows on Windows subsystem because there are still situations that your payload might have to migrate from a 32-bit process to a 64-bit process. And here we'll talk about how to transition through Heaven's gate to make it happen. Next module is about API hooking, how to use a modern and popular hooking library like Detours. But also we will do inline patching and import address table hooks on our own. The last module will briefly cover simple methods of controlling your payload execution and how to make sure that only one payload is fired, okay? And finally, we will use most of these techniques in a combined project where you will be targeting a real application to steal password without using keylogger. So, buckle up, boys and girls, it's gonna be a fun ride! First, download the VM image and zip package from the course website. After the download, now we need to import the VM into the VirtualBox. So we click Import. Now we need to select a file, click Open, and Next. Then set up a machine base folder and click Import. So now VM is being imported and we will come back when it is done. The next thing we need to set up are shared folders. So click Settings, go to Shared Folders, click Add, set up folder path, choose your folder name, click Auto Mount and set up the mount point to Z drive, click OK and OK. And please note in the description of the VM there is a username and password for login to the VM. So now let's start the VM. Now we log in. Please note that this VM is a Windows 10 Enterprise Evaluation version available for download from the Microsoft website. The next thing we need to do is to unzip our course materials. So go to our shared folder and extract the zip. So we copy and paste. And after the unpacking process, our VM is ready for the course, so we can start. Hello and welcome to Red Team Operator Malware Development Intermediate course. My name is Renzo and I'll be your instructor in this course. This course is a continuation of Malware Development Essentials, but it's not mandatory to take it before this one. if you know the basics about PE files, string obfuscation, code encryption, classic process code injection, and how to program and compile C applications, you're good, all right? Otherwise, I recommend to check Essentials course first. So in next few hours, we will cover more advanced techniques. We will start with discussing PE file format in detail because we want to implement a custom variation of GetProcAddress and GetModuleHandle functions. And this will take us to creating a PE binary without any imports. We will also talk about variations of code injection, but this topic is huge and probably we could spend the rest of the time to discuss only code injection because there are so many different flavors of this tactic. So we will focus on about 5 of them, all right? Then another big one is ReflectiveLoader and how to create reflective DLLs, both from source code and from binary only. We need to cover Windows on Windows subsystem because there are still situations that your payload might have to migrate from a 32-bit process to a 64-bit process. And here we'll talk about how to transition through Heaven's gate to make it happen. Next module is about API hooking, how to use a modern and popular hooking library like Detours. But also we will do inline patching and import address table hooks on our own. The last module will briefly cover simple methods of controlling your payload execution and how to make sure that only one payload is fired, okay? And finally, we will use most of these techniques in a combined project where you will be targeting a real application to steal password without using keylogger. So, buckle up, boys and girls, it's gonna be a fun ride. So let's talk about how a loader finds the addresses of functions exported by a DLLs, all right? So what loader does, it takes the PE header of our DLL, parse these headers, get to the export directory, all right? And in export directory, there is a structure which looks like this. And in this structure, there are a couple of more interesting fields than others, okay? So first, there are 3 pointers to 3 arrays. The first array holds addresses, like RVAs of functions, which are exported in the DLL, okay? And this array is called export address table. The second array holds pointers to the names of the functions which are exported, all right? And the third array is, it's an array of indexes to EAT, to export address table. But for now, just remember that this is an array of numbers, okay? So the first array is array of pointers, the second one is array of function names, and the third one is the array of numbers. That's what you need to remember right now. There is also number of functions field, which holds the number of elements in the export address table. So the number of exported functions, all right? And there is also number of names, which is the number of elements in both the array of function names and array of these strange numbers, all right? So these 2 arrays, the sizes of these 2 arrays are similar. And lastly, there is also a name field holding an RVA to a string with the name of the DLL, all right? And there is also a base field which holds another kind of number, and this is the first ordinal number of the DLL. So let's take a step back. The DLL can export functions in 2 ways. It can export them by name, so you can see, this particular name like GetProcAddress or load a library, right? But DLL can also export functions using ordinals, which are just basically numbers, okay? And this base field holds the first ordinal which is exported from that DLL, We'll get back to this later. Now let's see how these three arrays correspond and how the parsing is done. So we had three tables pointed by a structure in export directory. Now, how does a payloader parse these arrays? So let's say I'm a payloader and my task is to find an address of a function called name3, okay? The only thing I know is the name of a function and that the address I'm looking for is somewhere in one of the three buildings I was redirected to from PE header, okay? So we have three buildings, top, middle, and bottom, or let's say blue, yellow, and orange, okay? And each building consists of rooms whose numbering starts from 0, okay? So we have room 0, room 1, room 2, room 4, room 7, and so on, okay? So what do? I go to the yellow building and start to check each room starting from room 0. So I go there and I see name 0, okay, which is not what I'm looking for. So I go to the next room, right, room 1, and check the name there. Same result, no hit, okay? So I move on to the next one and to the next, up until I find the room with the name of a function I'm supposed to find, okay? If I check all the rooms in the building and none consist, my function name, I get out and say, sorry, there is no one here who has that name, all right? But in our case, I get lucky and name3 sits in room 3, okay? So what do I do next? I take this room number, which is 3, okay? I get out of this yellow building, go to the bottom one, and I go straight to the room number 3, okay? This one. I don't have to go through all the rooms as I did in the yellow building because I have a hint that in room 3 of orange building there's some extra information awaiting and allowing me to find, and as an end result, to find the address of the name3 function, all right? So what I get there? I see number 4, right? Aha. So now I need to go to the top building and knock to the room number 4, all right? So I do that. I go to the room number 4, which is 0, 1, 2, 3, 4, and there's a reward for me, which is an RVA of a function name3, all right? So this is basically the process PE-loader goes through each time it wants to resolve an address of an exported function, okay? Now, what about the situation where I don't know the name of a function, but I know the ordinal of the function, okay? So in this case, my job is super simple. So let's say my ordinal to look for is 6, okay? Now I just take the base number from export directory, this one, okay? And let's say base equals 1, okay? I subtract that from my ordinal, that is 6 minus 1, which gives 5, okay? And that's the room number in blue building with an RVA of a function I'm looking for, okay? Of course, before I do all that, I need to make sure that the ordinal number is not less than base number and is not greater than total number of rooms in the blue building, okay? So it's not the ordinal number is not greater than number of functions in the export directory structure, all right? So that's basically how exports in PE files work. Now let's jump to a VM and take a closer look into one of the DLLs from Windows. And for this, we will be using our favorite tool, which is PEBear. All right, so let's parse kernel32.dll. All right, so we open up. It's in Windows System 32 kernel DLL, and let's use the same header file, winnt.h, and let's export directory. Okay, so we have it here. Okay, so we go to optional header. We find the data directory, and now we have found the address of export directory. So let's follow this. And what we have? We have first 4 bytes are characteristics, right? All zeros. The next one is timestamp, 4 bytes. Then we have 2 word fields, major and minor version. So 1, 2. Then we have a name, okay, name here. So it's 09415A, so we can check that. So it's 09415A, okay. And we can see this is kernel32.dll. All right, so this is the pointer to RVA to our name of the DLL. So this was this. Next we have a base, also 4 bytes. And the base is 1. So it means that the minimal ordinal number from that DLL is 1, right? Then we have number of functions, which is 065D. And 06, let's calculate that. So hex 065D. Is it correct? 65D. So it means almost over 1600 functions, okay, in the table. 06D, 5D, right. Then we have number of names, which is the same, right, like this one. And so all 3 arrays are the same size, okay. And then we have our 3 pointers to 3 arrays. Like this one is for export address table. This one is for the array of function names, and this one is for our ordinals, number of array of numbers, right? So if you click export, you can actually see all this parsed already for us. So characteristics, name also points to, yeah, we've checked already. We've checked that already. Net base is 1. The sizes are the same, and we have our 3 pointers. Okay. Now, so let's take a look at, oh, we actually don't need that anymore. Let's take a look at array of function names, function pointers. So if we go there, the first element is 4 byte, RVA is 941.7F. So it's this one, okay. The second element is also 4 bytes, RVA 941.5B, which is this one. Then we have the third element, 01E860, which is here, and so on and so forth, right? If we go to array of functions, function names, we have these RVAs. So these are pointers to strings. So 094167, it's here. And if we go there, oh, we can go there from here. It is acquire SRW lock something exclusive. Okay. And then the next one is this one. The next field is here, 0941A0, and so on and so forth. Okay, so this column is filled with values from that array. And lastly, we have this strange, as I call that, strange array of numbers. It starts from 0, and each element is a D word, so 2 bytes. So it starts from 0, 1, 2, 3, 4, 5, and so on and so on. Okay. And if you add base 1 to each element from that, so the ordinal for the first function is 1, which is here. The second one is 1 plus 1, that gives 2, and so on. All right. This is how it looks. There's one catch here. If you take a closer look here, you might notice that some of the RVAs are particularly high. It's 941A7F, 941A5, right? Comparing to 1E, so these addresses are low, so to speak, but these 94, 94, 94, 94, 94 are sort of strange, right? So if we go there, so normally, if you click, so let's take add atom A, we land in text section, okay, and we are in implementation of that function, okay. But if you go here, follow, you land in our data, somewhere in our data, and actually this RVA points to a string ntdll.rtl acquire as our rw lock exclusive function. This means that if someone wants to call the function, this function in kernel32.dll, it will be redirected to ntdll.rtl to this function, okay? So loader or parser has to, when it finds that kind of string instead of RVA, it needs to go to that DLL, so load that DLL, the called forwarder, okay, and parse that DLL looking for this particular function and resolve address of that function and return the address of that function as the address of this function, okay. So that's how it works. And how does the parser knows or the loader knows that it's a forwarder and not like a regular, because you just can't tell that it's a forwarder or not. There is no special field stating that this is a forwarder or this is like an ordinary address. And the check is done really simple by checking if this RVA is within a range of export export directory. So if you take a look, so we are talking about 9417F, right? So if that RVA is within the range of export directory, this region, so this region starts from 190 and goes up to 9D DE something, all right? So if this address is within this range, it means it is a forwarded function, and it points to a string, not a real code, okay? That's basically how this trick works. You can also see the same information without PEBARE, but you can use dump bin, okay? So if you go to here and use that with exports parameter, so we Windows system 32 kernel 32.dll kernel. Let me pause this. So this is how it looks like when you parse all the data. Okay, so you have the ordinal numbers, right? The hints. So these are actually values from this strange array of numbers. Okay, these are called hints. And then we have RVAs of functions and the function names. And if any of the function is forwarded, then you don't get the RVA, because dumpbin doesn't do like the forward resolving. It will just say that this particular function is implemented within anti-DLL library. All right. So this is how you can use dumpbin to get the same information. So, yep, this is how you can parse export address table and find and resolve functions, function addresses. So now it's time to talk about an import table. Okay. So when the PE loader starts to load the module into the memory, it will at some point it will start to parse import address table, or import table actually. So it will go to PE headers and find the data and directory structure, and then jump into the import table, and it will there it will find the pointer to a memory region which holds an array of elements which are type of image import descriptor, like this one on the slide. All right, and from this this structure, there are actually only 3 elements which are of interest, of our interest. So the first is called original first thunk. It used to be called characteristics, but now it's just a union. So you can refer to this element using a new name. And this field points to, it's a pointer to something which is called import lookup table. Okay. The next field is first thunk, which points to another table or an array actually, and it is import address table. And the third element is a name, which points to a name of an imported DLL. Okay, so let's go to let me show you how it works in practice. So we have our one of our descriptors, and the characteristics or original first thunk points to import table. Okay, and the third thunk points to import address table. Now all these arrays or tables contain RVAs to something which is called hint name table. Okay, in hint name table, as the name suggests, it contains a pairs of a hint followed by a string with the name of a function. Okay, both tables actually point to the very same elements. So import lookup table and import address table, at the very beginning, the first element in this example point to get message, the second to load icon, and so forth. Okay, but at some point, when the parser starts to parse this information and starts to finding addresses of those functions, these addresses will be written into import address table. Okay. So how the parsing is going? The PE loader finds this record. Okay, checks the name of the library. It then takes that library, loads it into the process memory, and starts to parse its export table. okay, starting to looking for this information. And how it goes. It goes through import address table, tags the first element, reads the hint name, actually it reads the hint first, and hint, as you might recall from the export table module, hint is an index in the export address table. So if the loader is lucky and this hint is the right one, it will extract the RVA or the address of this particular message, particular function from the export address table, and it will write it into the first element of import address table. Okay. If it fails finding the address using hint, then it will just take the string, the name of the function, and it will parse the export address table as the same way as we described in the previous module. All right, and this process goes on and on. All right, and after some time, this table should be filled out with the right addresses, and the module is ready ready to work. Okay, so let's go to the VM and see how it works. Before we start parsing import address table, let's first try to figure out why import address table is used. So let's open notepad.exe and let's go to text section of that. Okay, so here you have a call to external DLL, anti-DLL, and it's calling NTW event write transfer function. Okay. So at the compilation time, compiler tries to resolve all the functions and all the calls during this process. But when the code calls the external DLL and external functions, compiler cannot know what will be the future address of that function in the memory of the process. Okay, so to resolve that issue, it uses a dedicated memory region which can be prepared during the compilation time, and this memory region will hold, it will be a table of pointers which will point to specific functions, and that is why this is what we call import address table. And let's open up our pbear and load up our notepad.exe notepad, and we can also load our WinNT header file. So let's find it first. Go here, WinNT. All right. We don't need this, we don't need this. Okay, and now we need to find import descriptor. Okay. So we go to optional header, to the data directory, we find import directory, and let's go there. So first record is 4 bytes long. It's original first thunk, or it used to be called characteristics, right? So this address points to our import lookup table, right? The next field is timestamp. It fills with the zeros. Further chain is also filled with zeros. The name is the next one, the next field in the structure. So let's see what the string, what kind of string is there. And it says advapi32.dll. So this is our first DLL being parsed. Okay. And the last pointer in the structure is first thunk, which points to our import address table. Okay. Now we don't have to do this manually. We have an imports tab here with all the already parsed information. So in this particular case, we have a lot of DLLs. Okay. If you want to know how many records are here, you can go back to optional header and check this. The size of it is 244 in hex, and from the definition we know that the structure is 20 bytes. Like 1, 2, 3, 4, 5. 5 times 4, it means 20 bytes. Okay, so to calculate the size of import table, we can use calculator. So 244 divided by 20, it means 29. Okay, so 29 records or elements in this table. But actually, if you count all of them, all the DLLs from the list, you will get 28, not 29. And the reason is that the last element in the array in this table is empty. So urlmon.dll is 20 bytes here, takes 20 bytes, okay? And the last element, which is 29th, holds 20 zeros, okay? So that is why we get 29 here. Okay, so let's get back to our import table. So let's see, 021820, it's here, so it's our original first thunk. The name of the DLL is here. You can verify it here. advapi32.dll. Looks good. First thunk, the value from here is also works, and then it's followed by the next record. So 021B8, which is here. The DLL name is here, right? And so on and so forth. So this is our import table, and the last thing which left is actually what these tables contain. Okay, so under first, so let's go from here. So this field, this points to a table, import lookup table, right? You can see it here. And so original thunk points to these values, okay? And these values are actually pointers to a hint name table we've seen on the diagram, right? For 64-bit architecture, each value is 8 bytes, and if we are dealing with 32-bit architecture, all the values are 4 bytes long. So this is our sort of import lookup table, and if we go to here, we see the same data, although it's under different address, right? But we see the same pointers. So we can see it here, compare it here. And it's expected, so this column resolves to our imports lookup table, and this is actually our import address table. Actually, this is this one, and these are just values from that table. So where these values they point to, let's see it. And now you see the hint name pairs. Okay, so the first 2 bytes are 0 to 15. So it is our hint from here. And let's put it here, maybe. And then it's followed by the name of the function, which is open process token. Okay, the next is 10170, and it's get token information function, and so on and so forth. Okay, so this is how import table and import table is parsed, and you can view it on any other DLL. So let me show you how this table is being filled out by the PE loader at loading time. So let's go back to our debugger, and let's first change the preferences and a break on DLL load. Okay, and let's open up our notepad.exe again. So now if we go to text section of our notepad, we are in a notepad, right? So now you cannot see the name of the function resolved, right? So again, if we go here, we see our import address table, which is not filled with the right addresses. Why? Because there are no DLLs loaded yet, because we set the breakpoint at library load time. So anti-DLL has been loaded, and that's it. And so let's continue. So let's run. Kernel 32 has been loaded, kernel base DLL, the VAPI, and so on and so on. And we have to click 28 times, actually 27, right? You can see still that this table hasn't been loaded yet, like filled yet. And one more time, and now it's system breakpoint. So if we get back to our import address table, now it looks more familiar. Okay, and if we go back to now we can see this this function being resolved, right? So it points to anti-DLL anti-DLL library. Okay, and let me show you one thing. So import address table can work in 2 ways, or these can hold 2 types of pointers. One pointer can be a direct pointer to the DLL. Okay, so it's an actual address of the function, or in this particular case, which is get text metrics w function. This is actually a pointer to a sort of jump table, which actually points to the right function. So it can work both ways. All right, that was import address table. So now it's time to look into the first template, our code template. So let's go to our course materials and open up implant.cpp. Now, you might recall from Marvel Development Essentials course that this is a standard template for the implant. So, quick recapping. This is our EAS decryption function we use to decrypt our payload, which is here. It's a 64-bit notepad with here's the key for the decryption. And what we do, we use virtual alloc and move memory function pointers, which are dynamically resolved using GetProcAddress and GetModuleHandle. And we use these functions then to allocate memory. Okay. Then we decrypt our payload with our AES decrypt function. We copy our payload into already allocated memory. We change protection settings on this region to be executable and readable instead of read-write. And then we start a new thread with our payload. Okay, that's basically what this code does. Now, in previous course, we were talking about using dynamically resolved functions instead of using them statically compiled and linked into the P file, so that we want to avoid some kind of heuristics, and we don't want to expose too much functions in our import address table of our implant binary, right? So for that, we were using GetProcAddress and GetModuleHandle. Now, how to implement? So let's say we want to hide also these two functions. What we can do? Can it be done? Yes. And what we need here is our own implementation of GetProcAddress and GetModuleHandle. Okay. And I've already included these calls here. So let's comment these two lines out and uncomment these. They are called help GetProcAddress and help GetModuleHandle, and they are implemented in a separate file. So let's save that and open helpers.cpp. And here we have it. So the first one is GetModuleHandle. We will cover it later. For now, let's take a look at GetProcAddress. So if you take a look at these structures and pointers, you should be already familiar with that, because we were just discussing this for the last an hour or something. So what we are basically doing here is we extract all the information we need from PE headers from our file, okay, from our module. So first, the base address is taken from the parameter. So when GetProcAddress is called, we get the base address of the DLL we are looking for. So this is stored in a local variable based adder, and based on that we can now parse PE headers. So at base address, the image.header structure resides, so we store it as a pointer. Then from .header we can reach to LFA new field, which holds RVA address of the anti-header structure, right? And keep in mind that everything we extract from these fields, these are RVAs. So these are just offsets in the memory of the process. If you want to have the virtual address, you have to add to the RVA, you have to add the base address. Okay, so everywhere in the code, this kind of sum will happen. Okay, so once we have anti-header, then we reach out to optional header. Okay, we get the optional header, then we reach out to data directory, and specifically we are looking for the export directory. So we are going to parse export address table of our DLL. So we get that, and from that we calculate the actual address of the export directory. Okay, because you might recall this structure has only two fields: the virtual address and the size. So we extract the size RVA from that field, we add our base address, and we get the address of our export directory. From that, we can now get the pointers to three tables. Okay, the first table, address of functions, which is export address table. The second table is the table of names, and the third one is what I call hints table. Okay, then we have our variable, which hopefully at the end of this function will get, you know, the virtual address of our function we are looking for. So this function, and we start to parse. Now we can look for the function either by function name or by its ordinal. So if it's the case of ordinal, we have to check that if proc name parameter actually holds the ordinal, not the function name. So how we do it? We just right shift the name by 16 bits, okay, which is 2 bytes. And the reason is that 2 bytes because the ordinal it's a word variable, so it takes 2 bytes. So if we shift right by 16 bits, and if we get 0, then it means that we are dealing with ordinals, not names. Okay. So in that case, what we do, we need to convert that into the so to speak number by just masking the first 2 bytes of that variable. We get this number converted. And we also extract from export directory, we export the base, okay? So which is the first ordinal number in our DLL. And the reason we do that is that we need to check if this ordinal is actually implemented or exported in our DLL, okay? And we check that by checking if either ordinal is smaller than base, okay? Or if it's higher than base plus the total number of all exported functions in that DLL. Okay, so if that's the case, then we need to return null point because basically this ordinal function is not in the DLL, right? But if we pass that check, then we can simply jump into export address table using ordinal, but we need to decrease it by the base. And this calculation gives us an index in export address table. So we extract RVA of that function, we add the base address, and we have our function address in this variable. So that was the case with ordinals, calling functions by ordinals, okay? If we are dealing with normal function name, then what we basically do, we go into the for loop and we are starting to check the function name table one by one and just compare, you know, our function which we are looking for with like a current function extracted from the table. And if we found what we are looking for, then we take the index of current index, so I, we take that index to our hints table and extract another pointer or another index from that table, and that index is used in export address table. And again, we extract the RVA from export address table, add the base address, and we have our proc address stored. Now, it would be almost over, but yet we have to we have another case. Okay, if our RVA is actually a forwarded string in this form, library.function. Okay, so how do we check that? We simply take our proc address we have found earlier and check if it's within the range of our export directory memory region. If it is, then our function is actually forwarded to other external library. Okay, so if it's not, we just return our proc address and we are done with that. But how we deal with forwarding? So we know our RVA. We know the address of this string, like library name dot function name. Okay, so what we need to do here, we need to extract this library as a separate string, extract that as a separate another string, like another variable. Then we will load that library into the memory of the process, and we will start parsing that library looking for this function. So we will call recursively, we will call our function again, but this time on this particular library. Okay, so let's go through that code. So we define two variables, forward DLL, which will store our library name, and forward function, which will store our function name. And for the forward DLL, we use string duplicate function, which will make a copy of that string, okay, store it somewhere on a heap, and return a pointer to that copy of that string. Okay, so now our forward DLL variable points to letter L. Okay, now the next step is to extract that string. So how we do it? It's a simple trick. So we use a string chr function, which tries to locate the first occurrence of the dot in the string. Okay, so it takes our library.function string, and it starts to look for the dot. Once it's found, it will return the position of that dot character. Okay, and it will be stored in our forward function. Once that's done, the next step, what we are doing is we write 0 byte in the position of the dot. So after this operation, our string will look like library 0 function instead of library.function. Okay, and we are almost ready. But you have to keep in mind that forward function variable is actually pointing to the 0 byte, not to F letter. So we just have to increase it by 1. And after that operation, our forward function points to F, to the first letter of function string, and forward DLL is pointing to letter L of the library string. Okay. Now we are ready to actually resolve function in external DLL. So how we do it? We call again help get proc address with kernel DLL. So we resolve load library function and store it in this variable, and this is a global variable. It's declared here, okay. And when we have that function, we can actually call and load our DLL. This DLL, we can load it into the memory of the process. And once that's done, then we can resolve the function we had here. And after that operation, we should finally get the real virtual address of the function we were looking for here. I know it's like, if you look at this, it seems to be complicated, but if you go through this slowly and read it, you will finally get it. It's not that hard. So once we have that, now we need to cover our own implementation of GetModuleHandle. Now to cover that function, we need to understand what is process environment block and how to parse that. So let's do this. So in Windows, there are a couple of structures used during runtime which contain information about threads and about processes. So one of them is called tab. The other one is called peb. Tab is thread environment block and peb is process environment block. So let's take a look at how they are defined. So we need to go to one of the header files. So again, we go to folder. Let's use, and they are defined in winternal.h. So if you scroll down, you will find peb structure and tab structure. Now if you take closer look, it seems really odd, right? This one has a lot of reserved fields, okay, apart from process environment block like DLLs slots, and a peb is similar. And this is really weird, right? And the reason is really simple, and you can find actually the explanation in the header of this file. This says this module defines the internal NT-APIs and data structures that are intended for the use only by the internal core Windows components. These APIs and data structures may change at any time, are subject to changes from one Windows release to another Windows release. To maintain the compatibility of your application, avoid using these APIs, okay, and data structures. So that is why Microsoft doesn't want the developers to use these structures in their code, because they change from time to time. So what we can do, we can actually use Windows Debugger to get more information about these structures, actually peb structure. So let's start Windows Debugger. Let's go some of these windows, we don't need them. And let's open Windows System 32. Let's open Notepad. Okay. So what you can do, we can view this structure using Windows Debugger, and with that simple command we get everything parsed already. So in peb there is information like if the process is being debugged, and yes, because Notepad is running under Windows Debugger. We have a list of modules, all the DLLs loaded into this process, into Notepad process. We have like information about the heap, what will the parameters, what's the current directory of the process, you know, window title, command line, environment, and etc. Okay, but this command bang pb is not what we're looking for. We're looking for actually the definition of the structure, and we have it here, and it's pretty big structure. And now you get it. We get much more detailed information about the fields. Okay, so we have inherited address space, some bit field, LDR, which is of our interest right now, process parameters, and many other information. So if you take a look at this and compare it to that, it's like, yeah, it's completely different. Okay. And this actually, this information comes from the PDB file, symbols file, which was downloaded into VM and are stored in symbols directory. Okay, so you can find these PDBs here. All right. So what do we do? We can. There is also a special sort of variable pointing where's the current PEB structure or object in the Notepad process memory. So with that, we can actually map that structure definition to the current object, and it will get filled with all the values from PEB of Notepad. Okay. So why we are interested in PEB? The reason is simple. We want to implement our own GetModuleHandle function, which should return the base address of any DLL we are interested in. Okay, and this information is stored in PEB. If you go to LDR or loader, there is another structure called PEB LDR data. There are 3 lists here. So we are actually interested in the second one. So if you click that, you see, so it's a double linked list. Okay, so it means that it's a chain of pointers pointing to 2 directions, forward and backward, like forward link and backward link. And they are like forming a loop. Okay, so if you parse this, if you go through this list in one way, at some point you will get to the start of the list, or you can parse it in backwards. That's okay. So how we parse that list? So there is another structure which is hidden under these pointers. So let's go back to our WinInternal header file, and this structure is called LDR data table entry. Okay, and this is it's defined here. But let's use WinDBG. So it's LDR data table entry. Okay, this is its definition. And so at the very beginning it has those, these 3 links, and then it's followed by the DLL name, a DLL base, entry point, full name of the DLL, and other information of the specific module. So let's take that address, copy, and parse that. And what we get, that under this address, the first object is pointing to our notepad.exe. Okay, so what's next on the list? Oh, excuse me, click the wrong button. Let me click this one. We actually need this. Now we have anti-DLL.dll, okay? And what's the next on the list? So let's check that out address. Kernel32.dll, and so on and so on. So if you go to, through each every member of that list, we can get the name of the module loaded and where this module lives. Okay, so the base address. So that's basically everything we need, almost everything we need, because there are two final points. First is keep in mind that this structure holds the name of the DLL in Unicode, so it's not an ASCII string. Okay, that's one thing. And the second thing is how we get to that information. To get to this information, we can use tab. Okay, tab structure. And in tab, there is a field called process environment block, which holds a pointer to our PEB. Okay, and on 64-bit architecture, this field is at offset 60. If we're dealing with a 32-bit architecture, this field is on offset 30. So we have to be aware of that. Okay. So let's jump back to our code. So now we are in GetModuleHandle, our implementation. Okay. So how we get the PAB? In 32-bit architecture, FS register has a pointer to tab. Okay. In 64-bit, it is GS register. Okay. On 32 is FS, so we reach out to using this function. We read FS and with offset 30. Otherwise, so 64, we read GS register and with an offset 60, which will get us the address of PAB. And once we have that, we can start parsing it as we did that manually in Windows Debugger. So if module name is 0 or null actually, so we just grab the image address base from the PAB. Let me show it again. At PB, we are getting this address from here. There's a field called image address base, and from that we get this address. So for our own binary, for our own module, we can extract that information pretty quickly. If not, then we just parse process environment block. So we take the pointer to LDR and we go to in-memory order module list. Okay, so this linked list, and we start to parse that in a for loop. So we go one by one and comparing the base DLL name with our name we are looking for. And if it's found, then we are just returning DLL base from that structure. So this is basically how this get module handle implementation looks like. So let's get back to our implant. And as I told you, we need to use Unicode strings. So you put capital L before the string, okay, definition. That's how you can define Unicode strings. So let's compile this. And finally, after many hours, let's run and see if it works. And indeed, it works. So, yep, that was pretty long road to understand, to implement your own GetProcAddress and GetModuleHandle functions. So we have implemented GetProcAddress and GetModuleHandle functions so that we don't rely on those which are implemented in kernel32.dll, right? Now, it should mean that our binary shouldn't be calling these two functions. So let's verify if it's true. So we use dumpbin for that, and let's see, find string get proc address. It's in import table. What about get module handle? It's also in our import table. So what is going on? Well, there are other things which happen when the process is starting. So there's some initialization phase, and compiler and linker add some additional code which prepares the process before the start. So let's see if it's actually the case, and let's open our implant. And let's go to kernel32 and get proc address. Let's set a breakpoint there. Okay, so do we still have that? No. Okay, so let's run it. And now we hit get proc address, but we see that this function has been called to resolve initialize critical section ex function. Let's run again. Now fls alloc, fls set value, another critical section, get value. So there are a couple of things happening before our our code is actually executing, but this is the code we're not controlling. Okay, now can we do better? Can we create a binary which doesn't have any import table? Okay, that's the question, and the answer is, of course, we can, and let's do it. So let's go to see the code, and this time implant is really simple. It's actually starting notepad.exe, so it calls create process function, and if you take a look, all the functions I'm using in this code are actually resolved by our helper helper functions. So we are calling all. So theoretically, this is not very different from the previous example, but here I'm instructing the linker that the entry point is our win main. Okay, and look what happens. So we go upwards and compile the stuff. Let's see if it runs. Yep, the process has started. Now let's use PEBear to see if there are any imports. Actually, we can use dump in as well. No, nothing. But let's open this implant here as well. And let's go to optional header. And as you can see, import directory is empty. All right. So it means no import table. But there is one catch here. Let me show you. Let's open up helper. So if you recall from the previous helper, we were using several external functions. We were using string comparison function, which is case insensitive and compares Unicode strings. So I had to change that to this. And so from here, I have removed all the code responsible for resolving forwarding, function forwarding. And the reason was there are a couple of external functions as well. So can we do better? Yes, we can. One thing you can do is actually implement these functions on your own, okay? And which is tedious and error prone probably, but there's another thing that can be done is actually in the code. First thing what you can do is to get function pointers to the real getproc address and get module handle using your helper functions. And once you have them, you can use these pointers to resolve the rest of the functions, okay? So this is how you can create a binary without import table, all right? So let's move on to the next module. Another method of triggering code execution in a remote process is to use thread context. What is thread context? It is basically a bunch of information about the thread, okay, executing in the context of the process. And this information covers things like memory allocations, heap, where is the stack, what are the values of the registers, that sort of thing. So we can use that primitive to trigger our execution in a remote process. So this is how this technique goes. So we have a process with at least one thread executing in that process. Then we have to find that thread in the remote process. Once it's found, then we allocate and copy our shellcode into the remote process, and we can use many techniques for that. Basically, you can use a classic version, so virtual alloc and write process memory. Then we suspend the execution of the thread we have found earlier, all right? And we change the context of that thread. So by changing the context, I mean we change the instruction pointer register to point to our shellcode so that when the thread starts to execute again, it will jump straight to our shellcode and start to execute it. And that's exactly what resume thread API call does. We unsuspend the thread and it starts to its execution with a new context. Keep in mind that hijacking existing thread and its context destroys completely the work of that thread. So if the thread was doing something essential, then this work is gone. Okay, so let's go to the EVM and see how it works. So let's play with thread contexts. So we open up our template. This looks pretty much the same as the previous one, the classic one. The only added thing is this function. We'll discuss it a little bit later. And this is our inject context function. And the main, yeah, we are targeting Notepad again. So that's no change here. So in the context injection, so what we do, we need to find a thread, okay, using find thread function, and this function basically uses the same API as find target. So this one creates tool help 32 snapshot. So it's snapshotting this one snapshots the state of the memory and looking for the processes. And in find thread, we are actually interested in threads. So we get the snapshot, and then we go through the snapshot looking for any thread which is in our target process. Okay. Now injection, it looks like this. So we get that thread. We decrypt our payload, we allocate and write our shellcode there, nothing fancy. And then we need to suspend the target thread we have found. Then we get the context with this function. So we extract all the information related to the target thread. Okay, it's stored in CTX structure. And if we are running this code on 32-bit architecture, then we set in the context, we can, in this structure, we can set specific register. So in 32-bit version, it is EIP. Otherwise, in a 64-bit, it's RIP. Okay, so we point the instruction pointer to our shellcode, and this changed context is set on the remote thread, and finally we resume the thread. All right, that's basically how this technique works. So let's go, we'll compile this. Let's start Notepad. And we can actually pin this to the taskbar. And let's run it. So it is running. So we have successfully hijacked one of the threads of Notepad. Everything works. But there is one catch here, as we are hijacking one of the threads. So basically this means that the state of this thread is like unknown. Okay, so after our shellcode stops executing, we might crash the process. All right, and this is exactly what happens here. All right, so this, you have to keep in mind that that kind of technique might put the process, the target process in some bizarre state and eventually crash the process. All right, That was thread context injection. So far, we were using just one method of, to deliver our shellcode to the remote process. But there are other techniques which does pretty much the same thing. And one of them is creating a views on sections of memory. And this is a classic example of IPC, or inter-process communication, when the two processes wants to share a region of memory between them, okay? So we can use that mechanism for our code injection. And actually, this mechanism doesn't copy the shellcode between the processes, but actually the remote process has access to our shellcode, okay, so to speak. Let's see how it looks like. So first step is to create a section, which is basically a new region of memory in our own process. And to access this section, we need to create a view in our own process. So we can access that region through the view. After that, we copy our shellcode to this section using view, local view. And after that, we also create a remote view of that section in our target process. So after that operation, Explorer.exe can access our shellcode using a remote view. And after that, we execute the remote shellcode using any known triggering mechanism we discussed so far. Let's jump to the VM to see the code. So let's put view of section into action. All right. So first, let's open up our code. This is standard stuff. Find target, find thread. We've already seen that. We are also targeting, we are still targeting notepad.exe. Okay. We decrypted our payload here, and then we call inject view. And this goes like, first we resolve the anti-create section function. So with that, we can create a new section, so sort of memory region in our process. It has execute rewrite permissions, and it's already committed. So then we create a view with a call of, through the pointer, calling through the pointer, which gets resolved with GetProcAddress. With that, we have a pointer to our memory. Then we can copy our payload into this new section through using the view, okay, local view. And to deliver, so to speak, to deliver the shellcode to the remote process, which is pointed by this handle, we create another view, this time in a remote process. And we get the address of the remote view in this variable. Okay, so we use the same function, anti-map view of section. Here, the second parameter is the handle to the process in which the view is created or is supposed to be created. So the local one we use just with that function, get current process, and in the remote case we use handle to the remote process. So after that we call our shellcode in a remote process. Before we compile that, let's set some printing so we can investigate it further. So let's save that and let's go to compile, run notepad, run implant. So the notepad has been found, bit 1404. So this one. And now we have the addresses. So this is the address of the payload in our implant process. So let's do this. 4E. So it's this. Okay, so this is our decrypted payload. Then the local view address is 20 C. So it's in here. C6 7D 7E. Yep, this is the one. And let's see if the same view can be found here. 2875 D9 3. This one. And yep, so notepad.exe can see our shellcode. So now if we hit enter, shellcode has been executed. Yep. All right. So that's how you can use views on sections to deliver your payload to the remote process. So let's talk about asynchronous procedure call, or APC. And before we go there, let's talk about what asynchronous execution is in general. So let's say your program wants to read something from the disk, like a file, okay? And usually this operation takes a lot of time. So what your program can do is, instead of waiting for the data, it can actually request, throw a request to the system saying, hey, system, I need that data from that file, but in the meantime, I will do something else, okay? And just give me a hint when the data is ready. So that's basically asynchronous execution, okay? Now APC is just one of the implementations of that mechanism, all right? So how we can use that? Well, APC is a good technique for triggering remote execution of our shellcode in a target process. So let's have a look how it works. So first, we need to find a thread in a remote process, all right? Then we deliver our shellcode to the remote process using any mechanism we know. And then we call a function called QAPC, okay? This function creates a APC object in the remote process, and the system will put that object in the APC queue, okay? Every thread in the process has its own dedicated APC queue. So after this is done, in our dropper, I call it wait and pray, okay? So we cannot do anything else, and we have to wait, because the thread we are targeting has to enter something which is called alertable state, okay? And this state is entered when our thread calls one of those 5 functions: sleep ex, signal object, and wait, and the other 3. All right. When they are called by our thread, then the thread gets into alertable state. And when this happens, systems fires up and says, hey thread, you have an APC object in your queue. Do something with that. So the thread will reach out to this object, and this object contains a pointer to our shellcode, and the thread will call that shellcode through this pointer. Okay, so our shellcode starts executing in the remote process, and after that we can celebrate. Okay, so let's do some experiments with that. All right, APCs. So the code, and the code is pretty much similar to the previous ones. We're also targeting Notepad, but now we use QAPC. So all the previous steps are similar. We find the target thread in notepad.exe, decrypt our payload, copy the payload to the target process, and then we queue user APC call pointing to the shellcode which is already in the process memory of Notepad. Okay, so this call will create this APC object, and it will be put into the APC queue of our thread, and then we have to wait until our hijacked thread will be set into alertable state. All right, so let's compile that. For compile, let's run Notepad and let's run implant. So our Notepad has IP'd 3388. So this is this one, and we don't see any indication that anything happened. We can actually try to verify if the payload is there. It should be there, but we can, yep, it is our payload. All right, so now we're in this wait and pray state I mentioned earlier. So now we have to wait for the action of the user to trigger that kind of alertable state on our thread. Okay, so we are talking about APC. So if we trigger, let's try to trigger some disk access, and yep, that might happen. So our APC probably got called, but for some reason, for some weird reason, it might get into some unstable state. So let's try different. Where is yes, it's here. So let's kill the process. Let's try different target. What do we have here? Let's use PE bear. So we are targeting PE bear. Compile. Run PE bear. Run implant. And see what happens. See if we can trigger anything. Let's load PE. And our shellcode got executed. Okay, so PE bear tried to access the disk, and this probably triggered APC call. So yeah. So as you can see, it works. And our shellcode got executed. So that was APC. Sometimes it might break something in the target process. So this technique is not very stable. as the other ones, but yeah, that's how you can trigger remote execution, in a target process using APC. There is also one small variation of using APC for remote code execution or code injection. And this variation is called EarlyBird. It's not like a pure code injection, since we are not injecting our shellcode into already existing process, but we are actually spawning a new process and then injecting our shellcode there. So it's not that classic approach. But let's see how this technique works, because it's pretty interesting. So let's go to the template, and it's actually defined in the main function. So what we do, we create a process. It can be any process, any binary here. I'm choosing Notepad, and this process is created in a suspended mode. So the loader will create a process, load our module there, anti-DLL there, and it will wait, and the process will be suspended, so no execution. Okay. After that, what we do, standard stuff, decrypting our payload, allocating and copying our payload into this new process, and then we queue APC pointing to our shellcode. So this looks like really like standard code injection, like using APC, right? But okay, let's run that and see what happens. So compile and run it. So I have put printf here to get some information back before we resume the thread. So resume the process. So we have this here, and so let's see this. Okay, so we have our implant, and the child process created from the implant is our notepad. It is in suspended mode. Okay, so it doesn't execute, and so let's see remote code if it's actually there. So it's 1A. We're looking for this one, right? 1A, 1FA, 9D, 98. Yep. So our shellcode is there. All right. So let's see what happens if we hit enter. So after we hit enter, implant will resume a thread in our target process. And yep, our shellcode had got executed. You won't see the notepad window here, which is expected because, well, actually it's not expected. So first of all, you should ask yourself why this happened, because in the previous module I told you that the process has to be in the alertable state, so the process has to execute one of those 5 functions. Okay, sleep X and others. So is it the case in when the new process is starting? Well, let's find out. Okay, so any left off here? Nope. Okay, so let's run it again, but this time we attach a debugger to Notepad, and let's set the breakpoint on that code. So go to expression, and yep, we landed in our shellcode. If you don't recognize this, let me show it to you here. So if you scroll down, you see the message from the message box. Okay. So let's set the breakpoint here and let it run. Hit enter. So execution inside notepad.exe has stopped on our breakpoint, so on our shellcode. So let's take a look at call stack, and you can see, the path that led to our shellcode. So our shellcode was called from this function. This function was called from this function, etc., and so on. So you can go backwards. And if you see here, there is a call to anti-test alert function. Okay, so let's go one step earlier in the function called loader initialize with some offset. Okay, and at some point this function calls anti-test alert or ZW. These are the same, and this is actually a system call. Okay, so after that we switch the context, so we switch from the user space to the kernel space, and kernel space actually is executing this test alert. And this test alert function is not actually documented, but what this function does, when it is called, it will empty the APC queue of the calling of the current thread. Okay, so this function also will trigger APC call. Okay, that's why our shellcode got executed without setting the thread into alertable state. All right, that was our EarlyBird technique for executing shellcode in a new process. There is also one small variation of using APC for remote code execution or code injection, and this variation is called EarlyBird. It's not like a pure code injection, since we are not injecting our shellcode into already existing process, but we are actually spawning a new process and then injecting our shellcode there. So it's not that classic approach. But let's see how this technique works, because it's pretty interesting. So let's go to the template, and it's actually defined in the main function. So what we do, we create a process. It can be any process, any binary here. I'm choosing Notepad, and this process is created in a suspended mode. So the loader will create a process, load our module there, anti-DLL there, and it will wait, and the process will be suspended, so no execution. Okay. After that, what we do, standard stuff, decrypting our payload, allocating and copying our payload into this new process, and then we queue APC pointing to our shellcode. So this looks like really like standard code injection, like using APC, right? But okay, let's run that and see what happens. So compile and run it. So I have put printf here to get some information back before we resume the thread. So resume the process. So we have this here, and so let's see this. Okay, so we have our implant, and the child process created from the implant is our notepad. It is in suspended mode. Okay, so it doesn't execute, and so let's see remote code if it's actually there. So it's 1A. We're looking for this one, right? 1A, 1FA 9D 98. Yep. So our shellcode is there. All right. So let's see what happens if we hit enter. So after we hit enter, implant will resume a thread in our target process. And yep, our shellcode has got executed. You won't see the notepad window here, which is expected because, well, actually it's not expected. So first of all, you should ask yourself why this happened, because in the previous module I told you that the process has to be in the alertable state, so the process has to execute one of those five functions, okay, sleep X and others. So is it the case in when the new process is starting? Well, let's find out. Okay, so any left off here? Nope. Okay, so let's run it again, but this time we attach a debugger to Notepad, and let's set the breakpoint on that code. So go to expression, and yep, we landed in our shellcode. If you don't recognize this, let me show it to you here. So if you scroll down, you see the message from the message box. Okay, so let's set the breakpoint here and let it run. Hit enter. So execution inside notepad.exe has stopped on our breakpoint, so on our shellcode. So let's take a look at call stack, and you can see, the path that led to our shellcode. So our shellcode was called from this function. This function was called from this function, etc., and so on. So you can go backwards. And if you see here, there is a call to anti-test alert function. Okay, so let's go one step earlier in the function called loader initialize with some offset. Okay, and at some point this function calls anti-test alert or ZW. These are the same, and this is actually a system call. Okay, so after that we switch the context, so we switch from the user space to the kernel space, and kernel space actually is executing this test alert. And this test alert function is not actually documented, but what this function does, when it is called, it will empty the APC queue of the calling of the current thread. Okay, So this function also will trigger APC call. Okay, that's why our shellcode got executed without, you know, setting the thread into alertable state. All right, that was our EarlyBird technique for executing shellcode in a new process. All right, let's talk about ReflectiveLoader. So ReflectiveLoader was developed about a decade ago by Stephen Fewer, but the technique itself was known earlier. Okay, the main idea behind this was to gain the ability to load a PE library directly from memory without using any file on disk. Okay. At some point, this technique was incorporated into Metasploit framework, which at the time, I think that they were using some different method, and I think it was called Patch App or something like that. But anyway, so when ReflectiveLoader came out, Metasploit team decided to switch to this new technique, and this technique is, is very powerful because your payload doesn't have to reside on disk and can be, loaded and live only in memory. So you automatically bypass any AV engine scanning files. Okay, but also you don't have to rely on pure code when you develop your payload, and instead you can do it in higher programming languages. So it, I would say, automagically becomes sort of position independent. Okay, so let's dive into how does loading reflective DLL work. So reflective DLL is a specially crafted dynamic library which contains its own PE loader, and this loader is exported as a function called ReflectiveLoader. Once this function is called, it starts to from resolving few functions it will need at the beginning. Then it allocates some a new memory region in the process. After that, it copies its headers and sections from itself from attack DLL. Okay. After that, it goes through the import table of attack DLL and resolves all the functions needed by this DLL. Of course, it loads all the needed DLLs as well, and then after that, it will fix all the relocations in a PE file, okay, in memory. And after that, it calls the entry point in attack DLL, so it calls DLL main. So this is basically how it works on a high level. Okay. Now let's go to the source code and see this process step by step. All right, so we are in Stephen Fewer's GitHub. And this is the original code written by Stephen. It's old, but it's really beautiful. If you take a look at this, it has a lot of comments. It's well structured. Everything is pretty clear. So let's go through this. So at the beginning, we call ReflectiveLoader function. And this is the main function of our DLL, ReflectiveLoader. So at step 0, we calculate our position in the memory. And it is done by simple trick. We call the caller, and caller actually is just it calls another function, intrinsic, so-called intrinsic function. So it is a function which is built into the compiler, and the compiler during the compilation just puts this function inline into the binary. Okay, and the return address basically returns the return address of caller, and it is taken from the stack. Okay, so when this instruction is executed, CPU will save the next instruction's address as a return address on the stack, and this function is basically extracting that address from the stack. Okay, so at this point we know where we are in the memory. All right, and then we loop through the memory backwards, searching for our image-based address. Okay, so in other words, we start from here and we go byte by byte upwards. So we're decreasing our pointer, and we're looking for the DOS image signature. So the MZ magic value in the memory. When it's found, to make sure we jump into the PE header, or in other words anti-header structure, and we check if there is a PE signature there. So if it is, then we have found our module's DOS header in memory. Okay. Once that's done, the next step is to process the kernel's exports. So we are going to locate virtual addresses of few functions in memory in kernel 32 and anti-DLL, and we do this using a process environment block. Okay, so this part of the code you should be already familiar with. So we read out the tab and we extract process environment block into this variable. Then we jump into the loader member of the structure, and from there we jump into the linked list in memory order module list. So we take the first member, and we start to iterate through this. So we get the name of the DLL, okay, and here we are looking for kernel 32.dll, but in this implementation, comparison is not done using strings, but it is using some kind of hash. So from that, we calculate the hash of the DLL, okay, and we comparing it to the already computed kernel 32 hash. And if we have found that, so we go to its export directory, okay, and we want to find its a few addresses from that export address table, right? So this part of the code should be already known as well. And what we do here, we look for three functions: load library, GetProcAddress, and virtual alloc. Okay, these three, and that's it from kernel 32. And from anti-DLL, we are looking for another function which is called anti-flush instructions cache. Okay, instruction cache. And yep, and that's it. If we find all four functions, then we break out and we go to the next step, which is loading our image into a new location in memory. So what we do, we create a new memory region with a virtual alloc. Okay, this memory region is execute read write. All right, then we copy our headers into this new region, and this is actually copying. In next step, we load all our sections. So how we do it, we have to locate section headers, and we're doing this by optional header plus the size of the optional header. So if you don't recall, we know the location of the optional header is after the anti headers or a p header, and we from p header we know the size of the optional header. So we have this pointer plus this value, and we land in sections header. Okay, so this is this instruction, and then we start parse section headers. Okay, so we get the address, we get the address of the data, the size of the data, and we copy this data into value b, which is here, right? So no, here. So excuse me, here. And after that, the next step is to fill out to resolve all the functions from import table. All right. So we go to import directory, we get the address, and we extract load the first library from which is listed in import table, and then we start parsing import lookup table in our module. In value A, we save import address table. So the table we want to fill with resolved addresses, right? And the next step is to actually extract the address from the loaded library, loaded here. So what we do, we reach out to export table of that module, of that library, but we do it only in case we are dealing with ordinals. Okay, so let me get back here a little bit. So as you recall, you can import the address, the function either using ordinal or name. Okay, and the check here in case of ordinal is done using image ordinal flag, and this basically means that if this value has the most significant bit set, this implies that this value contains an ordinal. Okay, and if that's the case, we go to export table of the library, and we extract the address of the function directly from export address table of the library. Okay. Otherwise, we are dealing with name of the function, and instead of playing with export table, we just use GetProcAddress and ask the system to resolve that address for us. Okay, and we save that address to import address table. All right, and yeah, and we parse all our import table up to step 5. So at this point we have allocated new memory. We've copied all the headers and sections, and also resolved all the functions in import address table. Okay, and now it's time for relocations. And up until now, I haven't covered that yet. So let's jump back to the VM and play with PEBear to see how the relocations work. All right, PE relocations 101 crash course. So first of all, why we need relocations? So nowadays, binaries can be loaded at any address in memory, although they contain some kind of preferable image base compiled into the PE headers, all right? So it still means that some parts of the binary might refer to the original image base by absolute addressing, and this implies that when such binary is loaded into memory, it can crash at some point because of these, so to speak, hard-coded addresses, okay? So to address this problem, Linker adds a so-called relocation section, which is, we can say it's a kind of map of where these hard-coded addresses live in a binary, all right? So let's take some example and to make it more clear, all right? So let's start PE-bear, load some example binary, which is Notepad, and let's go to optional header. So in optional header, we have image base, okay, set to this value. So it means that loader should try to load that at this address, but also in optional header, there is information that this module can be loaded at any address, okay? So the loader doesn't have to comply with that value and can load that somewhere else, all right? So let's start Notepad and see where it was actually loaded. So let's go. So this is the base address of Notepad instead of this value, all right? So that is why we have a relocation section which contains anything referring to this base address. So let's go to base reloc pad and let's see how it looks like here. So what is this? Relocation section is basically a set of blocks which are of type this image-based relocation. And so each block contains this structure and is followed by some 2-byte records, containing more information. So in other words, each block is a specific map with locations of where the relocation should be applied. Okay. So the first 4 bytes is the virtual address, and this virtual address is basically an RVA of specific page. Okay, in memory. Then the next 4 bytes is our size of the block, and this size of the block also contains the size of the structure itself. So in our case, it's 178 in hex, but the data after the structure is actually 170. 8 bytes is taken by the structure. All right. Now, what about these two byte values? So each record is means 2 things. The first is a type of the field, and these types are defined here. So it can be, this is just a bit set in this record, in this value. So in our case, it's A, which is 10, and it refers to, so it's related to 64-bit field. Okay. The rest of the value is the offset from the beginning of the page. So in other words, virtual address is the address of the page, and the offset from the value, shows you the exact location within that page where the relocation has to be performed. Let's see what lives here. So at this RVA 1C000 we have some pointers, and these pointers, as you can compare it to the original image base, they contain something like this: 01, 40, 02, 48, D0. Okay, So in other words, it's somewhere at the offset 0248D0 starting from this base address. Okay, so whenever code refers to this address, it will break because our base address is different. And that is why we need to do relocation. And how the relocation is done? So we need to calculate, the first step is to calculate the delta between these two base addresses. So originally Notepad, in its P header, it has this address. Yeah, this is our image base. Yep, this one. But Loader has loaded Notepad at some different address. Okay, so we need to calculate the delta, and then this delta will be added to this specific address. Okay, so let's do this. Let's take, where is that? Let's take this fire up calc and calculate the delta. So this is our base address, the real one, -140,000,000,000. Okay, this is our delta. So let's store that. Now let's add this address. So +140,024A-D0. Okay, and so let's go to actually do this address and see what is there. It's 7A34. This is this block, and AD0. Okay, AD0. So let's put some data here. Okay, and now let's start debugger, attach to Notepad, and let's go, where is that? Well, let's go to copy base address, go to expression, and we need to go to offset 1C000. Okay, so +1C000 to see this relocation table. Okay, and let's verify 7F F6 C3 is E3 4A C7 E3 4A D0. So it's correct. It has been correctly recalculated, relocated. And if we go to, we see our changed, like overwritten bytes. Okay. So basically what Loader is doing is going, let me get back to this, is going through all these blocks and add the delta to all the addresses from these offsets. So basically this is how PE relocations work. All right, so once you know how this works, this part of the code should be pretty easy to understand. Okay, so we calculate the delta. Okay, so our current loaded address subtracted with the image base from the optional header. All right, And we then jump to the data directory and looking for the relog section. And if it's there, then we start to parse it. So we get the first block, okay, first block, its address, and we calculate the number of entries in the block, so how many these 2-byte values are in the block. And then we start to go through all the blocks, all the values in the block, okay? So we check the type. If it's 64-bit, then we just add the delta to the offset. If it's high-low, which is 32-bit, then we add the delta. This part of the code is related to ARM architecture, and yeah, we skip that. We're not interested in this. We're dealing with Intel architecture. So other types of all the values, and basically this loop goes through all the relocations in our binary and fixes up all the all those values. All right. And after that, our DLL is ready to be executed. So the last step is to reach out to find our entry point, and before calling the entry point, we call anti-flush instruction cache function, which basically empties the CPU cache from any residue, code which wasn't updated before after our relocations, relocation calculations. Okay, so this is done, and we then just call our DLL main, and that's basically how this all code works. So, yep. That was a ReflectiveLoader source code walkthrough. Now it's time to use ReflectiveLoader in our code. So we go to, and let's open implant DLL.cpp. All right. So this DLL will be compiled as a reflective DLL. Okay, so it includes ReflectiveLoader.h and additional code from Stephen Fewer's GitHub repository. All right, and this DLL will launch a new thread with a function go. And this go function, basically what it does, it takes our encrypted DLL, which is encrypted payload, which is simple calc shellcode, and it will decrypt it and run it. Basically, that's a very simple thing. But that's only demonstration of how to use ReflectiveLoader source code in your project. Okay. And then after we compile this DLL, we will convert it, we will encrypt it again, okay? And we will insert that encrypted sort of payload into another implant, implant.cpp. And this program, what it actually does, it will decrypt the payload, okay, and resolve the address of the reflective DLL function exported by our implant DLL, okay, and then it will create a thread calling reflective DLL and ReflectiveLoader, and that function should start all the process I've described earlier. All right, so how do we find this ReflectiveLoader address in a binary. So I borrowed a code from Steven Viewer's repository. So that there is a function called GetReflectiveLoader offset, and this basically, this function, what it does, it parses export directory of that DLL, implant.dll, okay, and it will extract, it will search for the application, the function name here. So it will compare these two strings, and this string is actually defined here. Okay, so we're looking for the ReflectiveLoader function exported in our implant DLL library. All right, so let's compile this. So let's first compile our DLL. All right, and now we need to encrypt it. So implant.dll, and since this is the DLL, so let's save the output to some text file. Now let's open that text file and copy this into implant. So the key goes here, and the payload, so the encrypted reflective DLL goes here. We save that, and let's go to implant. Let's compile the implant, and let's run it, and our calc has popped up. But you don't have to believe me. So let's investigate if it works as intended. Okay, and let's do this slightly different right now, a little bit different. So let's put a breakpoint here. So this intrinsic function debug break will basically insert, so the compiler will insert int3 instruction, which is basically a soft breakpoint. Okay, so let's save that, and let's compile our program again. Of course, if you run it like this, it will not work, because the CPU gets to the int3 instruction, and this will generate an exception. And if the process is not running under the debugger, there is nothing to take over this exception and handle this exception. So the process crashes. But when we run this program implant.exe under debugger, debugger will handle the exception. Okay, so entry point, let's run it again, and now we have an exception, and this is the reason. Okay, int3, so this is debug break followed by create thread, sleep, and wait for single object. So if you take a look here, we have these three functions. So we are where we need to be. Okay, and now we need to get rid of that breakpoint. So hit space, and we just knob out this int3 instruction. Okay, and let's set the breakpoint on create thread and hit run. Let's hit run again, and we hit the breakpoint on create thread. And now if you take a look at the parameters of that function, we have 2 zeros, then it is followed by the offset to our ReflectiveLoader function, and another 3 zeros. So according to the calling convention, we have register RCX or RDX. These are first two parameters. R8 contains the third parameter, which is a pointer to our ReflectiveLoader function, and then R9 is also 0, and the rest of the parameters go through the stack. Okay, so let's go to our ReflectiveLoader. Okay, and let's set the breakpoint here. So run it, and we hit the breakpoint. Okay, so now let's see what is happening here. So we make some room on the stack for some local variables. Okay, and here we have a first call. So let's hit F7 or just step into. So 1, 2, 3, and this call, let's step into this call, as this function is pretty small. So if we step into, we see that some 8 bytes a keyword is read from the stack, right? This value, and this value is a return address of the function, of that function, right? So this points to 400.44c, which is the next instruction after the call. Okay, so basically this function returns the location of the code in the process. And if you recall from the code, this is exactly what function caller does. So this is how return address works. All right. Okay, so let's get out of that. We get back here, and now let's see what happens next. So there are some comparison. Now we read something from stack, and actually that address was our position in the process. Okay, so we step further, and now here this instruction compares EAX to 5A4D, which is MZ. So we check if MZ found. And this is exactly what we are doing in this loop. Okay, we are looking for a DOS signature, right? So somewhere later there should be a comparison to PE, and this is here. So let's put a comment, check if PE found. Okay, but since we haven't found that yet, so we jump, so we step over. Now we read out the current code position to REX register, and we decrement this address. We save that back to the stack, and we jump back. So in code, it means that we decrease our pointer we got from caller, and we start again. Okay, so this loop which looks for DOS signature. All right. So let's set a breakpoint here. So after it, or actually let's set the breakpoint here as well. So let's run it. Okay, and step in. So let's check. Actually, what is this? And as you can see, this is MZ. Okay. So our loop has found the beginning of our module in memory. Okay. Now, what we're doing here, if you recall, we found that, right? So now we are reading p header location in memory. All right, and this is 110. So if you add 110 to this address, it's here and it points to PE. Okay, so we have we have found our image. All right, so F9, we get here. Okay, and we know that we have found our image base. So now we jump out from that loop. And then if you now take a closer look, we are reading GS register with some offset 60. And this is our PAB. Okay, so in this address, we can actually check that here. So PAB is here, A2000, and it's exactly what we are looking for. So now we are starting to, this part of code, okay? And then there will be loader and so on and so forth. So I won't go through all this code under debugger, but I highly recommend to do that on your own and to see how all this code works and looks like in assembly. All right. So let's. Oh, before we close that, I want to tell you about one thing. First of all, if we go to our ReflectiveLoader DLL, let's list all the exported functions, and it exports ReflectiveLoader function, which is expected. Okay, that's the original code from Steven Feuer's GitHub. Now, the problem with that is that some security tools or AV engines even can detect that kind of string if you leave it on the disk. Okay, and it also resides in the memory. So if we search for pattern, ReflectiveLoader, it's actually in the memory, okay, of the process. And we want to avoid that. So how we can change that? I have modified the original code, and I have added one setting here. So this ref LDR name you can change to whatever name you want. Okay, so let's say stop trolling me. And the same thing you have to do in our implant loader, because this is the string we are looking for in the DLL. Okay, so we have to adjust that string as well here. So let's recompile that. Let's do this again. And so we need to copy the key. Put it here. As well as the encrypted payload. Okay, we can save that. Compile it again. And our break is here, so we can check that if it's gone from the process memory. So we start up debugger and open implant. Let's get rid of all the breakpoints. Let's run it. Let's run it again. We need to patch it. Let's run it again. Now we go to memory map and let's find pattern. And it shouldn't be there. Yep. So we got rid of this, so to speak, dangerous string from our binary. All right. We can actually execute that. See if it works. Yeah, it works. All right. So that is how you can use ReflectiveLoader in your source project. So what can you do if you don't have a source code of your DLL? Okay, you have a binary version of a DLL. What can you do? Can you load it reflectively? So Nick Landers from Silent Break Security, in 2017 he published an interesting project called Shellcode Reflective DLL Injection. And what he did was he took the previous work of Stephen Fewer and also a so-called improved reflective DLL injection by Dan Staples, who released an important update which was about allowing an additional function to be called after DLL main, okay, and supporting the passing of user arguments into said additional function. So now we can load a DLL, call its entry point, and then pass the user data to another exported function. All right. So that was what Dan Staples improved in a reflective DLL. And what Nick did was he actually built on that, and he created a tool set for making a binary, a DLL binary, existing binary, okay, to be reflectively loaded, and so to prepare it to be loaded in reflectively in memory, okay. So it works like this. It takes the existing DLL binary, okay, it adds the reflective loader on top of it, And before the ReflectiveLoader is launched, there is a shellcode edit called Bootstrap, which prepares some of the stuff, some stuff before the ReflectiveLoader takes control. Okay, so Bootstrap gets the current location and setups registers, then passes execution to ReflectiveLoader, which does its thing, and optionally allowing, after DLL main is called, then another function from the existing DLL to be called. Okay, so yeah, this is really interesting project, and let's go to a VM and see how this works. All right, let's jump to the code. So our implant DLL is almost the same as in the previous example. The only difference is that in DLL main we don't call any go function, and the go function is exported. Okay, so that's the only difference, and we are still launching calc shellcode, which is encrypted, and it's decrypted and executed in the go function. Okay, so in SRDI you can find the copy of the Nix project from GitHub. Okay, and we will be using Python toolset. So okay, so first let's compile our DLL. And now we need Python and convert. Let's see the options. So what we can do, we can set the function name which will be called, and actually if your function accepts a parameter, you can set it here. All right, and you can do additional things like clear header from the memory and obfuscate imports. All right, and some delay. But let's just do function name, which is go, and our implant DLL, and now we should have implant.bin, which is basically a binary blob, and now we need to encrypt it. Python AES and implant bin. So let's open our implant, our loader. And this loader is pretty much the same as in the previous example. So we copy the key, into here, paste, and copy this, and paste. Well, there is slight difference between this and previous example. We don't have to calculate the offset of the ReflectiveLoader, because what we have here is an encrypted shellcode. So we start to execute the first instruction, first byte, okay, instead of resolving and finding where the ReflectiveLoader function lives in the DLL. All right, so that's the difference. Okay, let's compile that. So let's go to implant and compile. And let's run it. All right, so our calc has popped up. but let's verify if it works as intended. And now let's do some small trick. So let's put here let's compile it again. And now we can run it again. So now implant is in the memory, but it waits for a key to be pressed. And so what we want to do is we want to jump into the process and see if it actually extracts our binary and our shellcode and finally the shellcode with the calc. Okay, so what we can do here, once we know that the process is like in a sort of suspended state, it just waits for the user input. So let's set a breakpoint using process hacker. So this is our shellcode. Yep, it's our first shellcode, which is this one. Okay, so this is already decrypted, and what we can do is let's go up. Let's first change the protection on this page to 40. So we want to make it writable. And let's on the first byte, let's set cc byte, which means in assembly it means int3. So now we have set a breakpoint on the first byte of this payload. All right. Now we can attach our debugger to the implant. All right. Let's let it run. And now let's hit enter. And our breakpoint has hit. So now we need to revert this breakpoint to the original instruction, which was E8. Okay. Now we see its call, but let's reanalyze the module. All right. And how do we know that it's actually our bootstrap shellcode from SRDI? We can actually check this in the source code. So let's go to Python and let's open up and let's see what we have here. So this is DLL main, and that's actually not the right file. We need to open this one. So function hash converts to shellcode. So this is actually the ReflectiveLoader 32-bit version and 64-bit version, and then bootstrap shellcode is constructed here. So let's compare. So we have E80000, so we have E8 4 zeros. Then we have 59, which is here, 49, 86, 89, C8, right? And so on. So we actually landed in the bootstrap code, which was what we wanted, okay? And so now let's see how we can actually pass all. We don't want to, go step by step. You can do it if you want, of course, but we want to stop the execution at the point where before our shellcode with calc get executed. So if you take a look at the source code of our implant, what we do here in Go function is we allocate the memory for the payload, we decrypt it, we copy it there, change the protection, and we call the create thread, okay, with that decrypted payload. So now what we can do here is let's set a breakpoint on create thread. So create thread, and let's see the call stack. Okay, actually, yeah. So let it run, let it run again, and see what happens. Calls are coming from like strange addresses which are not resolved by the debugger. Okay, and so let's double click on it, and if you scroll up, you can see wait for single object, create thread, virtual protect, virtual alloc. And if you compare it, this is exactly our Go function. All right, so if that's the case, then in register R8 should be our address of our shellcode, okay, since it's third parameter. So R8, let's see this in dump, and it looks familiar, and yep, it is actually our calc shellcode. All right, so if you execute, the calc is here. All right, so if you don't have source code to the binary you want to reflectively inject into the process, you can use SRDI project to convert your, so to speak, convert your DLL into a pure shellcode, which you can then load reflectively in memory only. All right. So far, we have discussed several options for code injection, either different methods to deliver your payload into the remote process, or several API calls to execute them remotely. Okay, so let's dive into this topic a little bit more. So let's go to folder number 4 and open up implant.cpp. Now this code is a basic template for injection, but this time it contains two types of payloads. Both are message box shellcodes, but one is for 64-bit process and the other one is for 32-bit process. So let's do a few experiments with that. Let's try these kinds of injections. So we are going to compile this implant as a 64-bit application, and we will try to inject 64-bit payload to 64-bit process, and the same with the combination with 32-bit application and process. Okay, so let's compile this. And our first test is to inject to 64-bit process, actually Notepad to be exact, but let's first see. So now our implant.exe is 64-bit, okay? So let's start Notepad and let's inject it. So that was successful, okay? So now we can check that that was successful. How about 32-bit to 32-bit? So first we need to compile it as a 32-bit application. So we need another command prompt for our compiler. So native tools 86. And we can actually pin that to the taskbar and compile. Okay, so now this is 32-bit app, and we need 32-bit notepad. So let's go to C, Windows, sys WoW64, and notepad. Okay, and let's pin this as well. And let's check the source code again. So 32-bit. Oh, okay, we need to check that. Change that. Okay, so let's compile it again. And let's run it. And it worked, okay. So these two cases are good. Now, what about 64-bit to 32-bit? So application is, the target process is 32-bit, so we leave these payloads, and 64-bit, so we recompile it here. And 64-bit, okay, so we need a target, implant, and this worked as well. All right, so good so far. So as in a joke, you probably now you know that it's not gonna work, right? So we are targeting, implant will be 32-bit, but we need payload 64-bit payload. So 32-bit. Yep. And payload 64. So we start 64-bit notepad, and nothing happened, right? Let's see if the payload got injected. So yes, we can see our payload. So it was successfully injected, but it didn't run. And notice the base address of that memory region. It is much lower than the other addresses. But let's take a look at the injection function. And so we know that from the process hacker, we know that this worked. Okay, so this, for some reason, that didn't work, and let's make sure. Thread handle equals, let's see what the value is of that. So let's recompile. Let's start afresh. Let's make sure it's 32-bit. It is. So the handle is 0. So it means that that call failed. All right. And yeah, you guessed that was expected. And to explain you why this is the case, we first need to understand how 32-bit applications run on 64-bit system. So let's do that. What's WoW64? WoW64, also known as Windows on Windows, is a Windows subsystem that works in the user's address space. In using WoW, you can run 32-bit applications on 64-bit Windows systems, okay? Microsoft actually did a lot to preserve, backwards compatibility with 32-bit apps, so that the older 32-bit applications could still work on 64-bit without a need to be, recompiled. Okay, so WoW64 is a sort of emulator which provides some sort of interface between the 32-bit version of anti-DLL and the kernel. And remember that the kernel runs purely on 64-bit. Okay. Now there are three DLLs which compose this WoW64-bit emulator. There is WoW64 DLL, WoW64 CPU, and WoW64 Win.dll. Okay. So the first DLL provides the core emulation infrastructure to access NTOS kernel binary, which is the main part of the kernel space. WoW64 CPU provides support for running x86 programs on x64. So this DLL is only related to Intel CPUs. Okay, for ARM CPUs there is a different DLL. And lastly, WoW64 the Win DLL provides access to Win32K, which is basically the GUI subsystem. So these are the only 64-bit modules loaded into WoW64 process. Okay, plus there are two versions of anti-DLL, 32-bit and 64-bit. So WoW64 is a normal 64-bit process. Okay, at startup, WoW64 DLL loads the x86 version of anti-DLL into the process and runs its initialization code, which loads all necessary 32-bit DLLs into the process. Okay, and almost all 32-bit DLLs are unmodified copies of 32-bit Windows binaries. So whenever a program like Notepad calls for anything within user space, execution happens in 32-bit mode, okay, more or less. But when a system call is needed, then the call gets redirected through 64-bit anti-DLL and lands in the kernel space, okay? And during this operation, process has to transition from 32-bit to 64-bit mode, and this transition goes through a so-called Heaven's Gate, okay? So let's have a look at it in the VM. All right, so let's take a look at our 32-bit process. So let's have a Notepad as our example. Let's close this. And so Notepad is 32-bit application, right? Let's take a look at the modules. So again, notice the base addresses. These are 32-bit, apart from anti-DLL. Okay, so we have two anti-DLLs loaded, and 32-bit and 64-bit, right? And we have WoW64 DLLs loaded as well. So WoW64, CPU, and Win, and all of them are 64-bit for 64-bit architecture. Okay. So let's see Heaven's Gate. So we need for 32-bit process, we need 32-bit debugger. Attach to Notepad. Okay. Let's wait a bit. All right. And now let's simulate. So let's take a look at how create thread function looks like. All right. So normally this would this function would actually enter into kernel space. Okay, so there would be a call to sysenter and with a specific number related to the system call we are calling, okay? And actually, let me show it to you. Let's do this. So let's open up another notepad and see the same thing. Here as well, as you can see, PDBs files are loading, so it takes a little bit of time. So again, the same thing, create thread, and this is how normally anti-DLL looks like. Okay, so we do we set some number in EAX and we call sysenter. Okay, we can close that. So in our case, 32-bit case is different. Okay, we call something like WoW64 system service call. Okay, so let's go there to see there is another jump, okay, to WoW64 transition. Okay, so let's go there as well, hit enter, and we see just one instruction, jump far 33 colon and some address, and this is so-called Heaven's Gate. So after that instruction, process will enter 64-bit address space. And I don't want to dive into too many details on this because we would need to go through virtual addressing and memory paging and page tables and stuff like that. But just keep in mind that to enter 64-bit address space, this selector number 33 in hex is used. Okay, if we transition back from 64 to 32-bit, then this selector is set to 23 in hex, and these selectors are stored in a CS register. Okay, now we are in 32-bit, so code segment register is set to 23, and after that jump instruction, we land into 64-bit. Okay, so once we know how this works, we need to understand how we can use that knowledge to make our injection successful. So we want to transition from 32-bit process into 64-bit process. And so let's go back to our code, and I have prepared one function which does this, but we need to jump into a source code of Metasploit, since this code is mainly taken from the Metasploit framework, and read through the source code of a few modules and assemblies, and it will be much more clear of what is happening here. Okay, so let's do this. How we can inject our 64-bit payload from 32-bit process into target process, which is 64-bit. So first we copy our payload to the target process, and we've already seen that it worked. Okay, but at the same time we cannot execute remote payload easily. We've already seen that as well. So instead of that, we first have to transition from 32-bit mode into 64-bit mode in our own process, okay, in implant.exe, and from 64-bit, then we can call a function which will execute our payload in a target process. So how do we do it? In our implant, we have two additional payloads. These are shellcodes, and execute x64 will allow us to transit from 32-bit to 64-bit mode, and in in the later mode, we will execute x64 function, which basically is an implementation of RTL create user thread function from NTDLL, and this function will call our payload in target process, in a remote process, okay? And the way we execute these two shellcodes is just by calling execute with two parameters, x64 function, and the second parameter is CTX or context. And context is a specially crafted structure which holds parameters for our create user thread function, because we have to pass to this function information like which handle to which process this call is referring to, where is the start address of our payload in the target process, and at the end we should get back the information about the handle to a newly created thread in a remote process. Okay, so these are basic steps of how to perform injection from 32 to 64-bit process. And now we can jump into Metasploit framework GitHub repository to see the code of both payloads execute x64 and x64 function. So let's go do that. All right, so we are in the GitHub of the Metasploit framework. And first we will go through the source code of execute x64 assembly. And yes, this comes from a migrate command. So you are probably familiar with that. So after a few minutes, you will deeply understand how this command works, okay? All right, so let's start. So we execute this shellcode by calling this in this convention. So it means that execute x64 gets two parameters. And since we are in 32-bit mode, calling convention in 32-bit mode is that parameters for the function are passed through the stack. Okay, so both function pointer and a pointer to a parameter will be passed through the stack. Okay, so we start, and so we do some standard stuff, making some room and preparing, saving the registers, and then these two lines, we take the parameters for the function. So we take pointer to the function and save it in ESI register, and parameter goes to ECX, okay, registers. Then we call delta, so we're calling this sort of function, but basically we are just jumping to this instruction, and every time you perform call, return address from that call is saved on stack. So with call pop combination, it means that EAX will get return address from that call, which means it actually will hold the address of its own instruction. Okay. So next step is we want to find our native x64 code, which is labeled here. Okay. And we do that by first calculating how many bytes are between native x64 label and delta label. So this is calculated here. And this value is added to EAX, which holds, the pointer to this instruction. So in other words, EAX now points to this instruction. All right. Then we make we allocate some space on stack, and we prepare to the transition to x64 mode. Okay, so we pass this x64 code, which is defined here, and this is code selector for 64-bit mode. And so we pass that through the stack, okay? And we call go all native, all right? And call go native is here. And in EDI, we save the return address from our call. So in EDI will store address of this instruction, okay, since it is the next instruction after the call. And we do the far jump, okay? So now we transition to a 64-bit mode, okay? And so eventually we start executing this, okay, instruction. And what we do, we just push RDI, which is a return address, which was saved here. And now we push it on the stack further. And we call RSI, okay? And what is in RSI? In RSI sits our function, okay? So the other payload we will be discussing next. And after this call returns, we restore our return address saved here. Okay, so again, it is address of that line, that instruction. And we jump back to 32-bit mode. So again, we take the code selector for 32-bit, okay, which is 23 in hex. And we perform the far jump. In RSP, there is address of our instruction, which is here, okay? So this transitions us into 32-bit mode back to this instruction. And from there, we just do some fix-ups. Yeah, eventually there was some bug on AMD CPUs, so these two instructions are supposedly to fix that. And we do the cleanup and return from our exec x64 payload, okay? So this is basically how it works. And by the way, the author of that payload is Steven Feuer, the same guy who created ReflectiveLoader, all right? Okay, so now we understand this payload. Now let's see how this works, okay? So we go to another file, this time remote thread. Again, Steven was the author of that. And so this payload will basically create a remote thread in our notepad in a target process by calling ntdll, the RTL create user thread from ntdll, okay? And this runs in 64-bit mode, all right? This function needs some information, okay? We passed the parameter, which I told you before. This parameter is just a pointer to a struct, okay? A structure specific, which has 4 fields: hprocess, which is a handle, LP start address, LP parameter, and hthread, okay? These four values. And why these 4 values? Because when you call RTL create user thread, you need to pass some parameters to that function. So we need to pass handle to a process we are targeting. So in our implementation, we are targeting Notepad. So this would be the handle to Notepad process. So this is passed in this field of that structure. We need to give it the start address, okay? And this start address parameter holds the address of the payload we injected into a target process, the 64-bit process we want to run our payload in, okay? And this parameter is passed from here. Third parameter is optional, so we can actually pass a parameter to our payload, okay? but it's not mandatory. And the fourth parameter we need to pass is actually the handle to the thread. So after this function returns this, as it's an out parameter, this parameter holds the handle to the remote thread we created. Okay, so we want that parameter to be stored in our context structure as well. Okay, so how this thing executes. So in RCX we passed a pointer to our context structure. Okay, a reminder, RCX. Okay, here ECX is basically an RCX are the same register. This is the reference in 32-bit mode. RCX is actually the register for 64-bit mode. So in this register we pass the pointer to our structure, and we pass it to RSI. Okay, and then we do some alignment of the stack, and we call start, which is here. Okay, and we pop RBP. So we already know that construction call pop. So we basically in RBP we will get the return address of the calls, which is something here. Okay, and this includes another file, block API.asm. Okay, I will briefly show it to you. It's in here, and basically what this code does, you can actually understand some of that already. So we are getting the pointer to peb, like GS, and with offset 60. Then we at offset 18 we get the pointer to loader, and another offset is the pointer to the module list. And we go through this list and start to look for anti-DLL module address, and after that we will go through the export address table of anti-DLL and try to locate the function we are interested in, which is RTL create user thread. Okay, so this is basically what this piece of code does. I won't cover it in more detail, but I encourage you to do that. It's a fun reading. Steven's code is always beautiful, very well commented. And just keep in mind that this code tries to find the anti-DLL and the function name not using the strings, but it calculates some hash to find these things. Okay, so most of this code is just calculating the hash. All right. So we are here. So we have in RBP we have a address of API call, right? This one. And what we do next, we set up parameters for our call here. So we have parameters like client ID, thread handle, start parameter, start address, etc., etc. So these are these parameters, okay, for the function we want to call. So these are set up here, all right? Then we pass in register R10, we pass the hash of all these two strings, and we call our RBP, which is this API call from this file, all right? So at this point, we basically call RTL create user thread, all right, with these parameters. And if it was successful, then we return 1 and we clean up and return. All right. So this is our x64 function. All right, payload. We are back in our injection code template. All right. So we have our payload 64 and 32-bit versions. Here we have a definition of our x64 declaration actually, how we will execute these payloads, and definition of our structure, which is used in as a parameter for x64 function, and our inject64 function. Okay, so I've included both payloads in a format of binary string. Okay, you can use that, and actually both shellcodes are encrypted here, since they are already known and AV engines are capable of detecting them. If you need the raw bytecode, you have them here as well. Okay. So what we do, we first create a memory region in our target process. Okay, so in our case it's notepad.exe, and we can actually change that to WoW64 already. So we open out notepad and pass the handle to that process, to our injector function. Then we copy our shellcode into the target process. Okay, and we will use these printfs to investigate step by step each, everything. Then what we do, we create a new memory region in our own process. All right, so these two virtual allocs. Then we decrypt our shellcodes for execute64 and WoW_ActiveX. WoW_ActiveX is our other name for x64 function. Okay, so we decrypt them both, and we create we copy them and then adjust the protection levels. And for x64 function, we also have to make it executable, readable, and writable, because it modifies itself during the runtime. Okay. The next step is to prepare the structure, our context structure for our x64 function. And if all is good, then we transition from 32 to 64-bit with that call, passing these two pointers. All right. And if this succeeds, then in context structure, we should get a handle to a remote thread, which was created by our function. RTL create user function creates a thread in suspended mode, so that now we need to resume it, and we can do that from 32-bit mode as well. And at this point, our message box should pop up. Okay, so let's do this. Let's go compile it. Make sure we're calling. Yep, we're calling 64. So let's compile this. Let's open up our notepad and process hacker as well. So to make sure our implant.exe is 32-bit, right? Now we can execute it. All right. So notepad PID 5156. This is this one. Remote code is at df 4 zeros. So let's go to memory. 40 F zeros. This is our payload. So it was successfully injected. That's good. And now we can hit enter. Inside implant, there should be two memory regions. allocated for our shellcodes. So let's go there. We have let's sort by this. Okay. So these are 100,000. So this one, okay, it's empty. This empty as well. Let's leave one of them. Okay. So hit enter. And if we reread, so this is our execute x64 payload, decrypted and copied into this buffer. All right. And the second one is the shellcode for calling RTL create user thread in 64-bit mode. All right. So this is this. So if everything is ready, if we hit enter, a new thread has been created. Okay. User create start. And now it's suspended. Okay. So if we hit enter, it starts to execute. And we can see that it started from this df0142, which is our shellcode, our message box shellcode, and we succeeded. It actually executed. So at this point, we can say that we are capable of injecting any combination of processes, both 32 and 64-bit processes. That's awesome. And now you know how migrate command in Meterpreter works internally. All right. Let's talk about API hooking. It is a generic way to change the way an application executes in memory. Okay. It was invented in a situation when one developer wanted to extend or add new functionality in a program whose source code was not available. And with API hooking, he could make the change at runtime without any modifications, of the binary. Okay. API hooking is also used by in game cheats. So let's say some player wants to become immortal in the game. And with hooking, he can intercept a function which checks the health of the player and make it return that his current health level is 100%. Okay. Even debuggers use a sort of API hooking. And let me show it to you. Okay, how it happens. So let's start a notepad. And let's hook a debugger. And let's go to a text segment. Okay. So we see a bunch of int3 instructions and followed with some other instructions. So let's see in Process Hacker how it actually looks like in memory. So we are in text segment. This is the right address, right? So we see the same bytes, CCC 4883 EC 48, etc. Okay. So let me set at this address, at address F with offset F, let me set a breakpoint here. And let's get back to Process Hacker and reread it. And now, as you can see, this byte has changed to CC. So it's 8BC2 48, and this 48 is not visible here. So in other words, debugger has changed the code of that application in this memory, but it hides it from from the person using the debugger. But in reality, in the memory, this byte has been changed. Okay. So what happens next if the CPU gets to this instruction? It will generate an exception, and this exception will be caught by the debugger, and the control will be given back to the debugger. Okay, so this is one of the examples how API hooking can work. Okay, and there are a couple of other methods of API hooking. We will experiment with Detours, import address table hooking, and patching code on the fly. So let's start with Detours. In 1999, two researchers from Microsoft, Galen Hunt and Doug Brubaker, published a paper called Detours Binary Interception of Win32 Functions. So let me, as an introduction, let me read a few sentences from that so that you can get some understanding of what Detours is. Innovative systems research hinges on the ability to easily instrument and extend existing operating system and application functionality. With access to appropriate source code, it is often trivial to insert new instrumentation or extensions by rebuilding the OS or application. However, in today's world of commercial software, researchers seldom have access to relevant source code. We present Detours, a library for instrumenting arbitrary Win32 functions on x86 machines. Detours intercepts Win32 functions by rewriting target function images. And the Detours package also contains utilities to attach arbitrary DLLs and data segments called payloads to any Win32 binary. Okay, this is really interesting functionality of the Detours. So what all this means? Detours. Let's go to some diagram. So let's say we don't have access to the source code. We have only a binary running in a memory, and at some point one function calls another function. So source function calls a target. For whatever reason, we want to intercept that call. Okay, that execution flow. So what Detours does, it will redirect this call to a detour function, which is controlled completely by us. So detour function can do whatever we want. Okay, it can read the parameters from that call. It can return whatever any value we want. It can jump somewhere else or execute something else. Yeah, it's completely up to us what we do here. And if we decide to continue the execution so that we want to pass the execution to the target function, it is done by something called trampoline function, which is a sort of proxy which makes sure that everything is set up correctly and passes the execution to the target function in a way that the target function is not even, so to speak, aware that any hooking or interception happened. Okay, and then target function executes normally and returns back to the source function. Okay, that's basically how Detours work. But there are also other API hooking frameworks and libraries available. So how this trampoline works? So at the beginning we have a target function, okay, which we want to hook, and a trampoline which is basically empty, so to speak. When we set the hook, we actually need to copy. So these instructions from the beginning of the target function will be overwritten by a jump to our detour function. And these instructions, overwritten instructions, are copied to the trampoline. So now trampoline looks like this, okay? And if we decide to, pass the control to the target function, so our detour function will jump to trampoline, starts to execute the original instructions from the target function, and after a few instructions, trampoline will jump to the original code in target function, okay? And the reason it is +5 here is that the jump instruction takes 5 bytes, and it happens that these five instructions also take 5 bytes in memory of that function. So if we override 5 bytes with jump instruction, we have to back them up, and then we can jump back to this from trampoline. We can jump back to it with an offset of 5, okay? So that's the reason. Originally, Detours was a paid framework, okay? So you had to pay a lot of, I don't know, it was like thousands of dollars to use that. But nowadays, Detours is not only supporting 32-bit Intel architecture, it also supports 64-bit and ARM, and it is also open source, okay? So we will use that as a good example of how you can use such hooking library in your projects. So let's get back to our VM and see the example. All right, let's take a look at the code. So we have two programs, one exe, one program, and hooking DLL. So our target program is super simple. It will just print 3 message boxes on the screen, okay, with these 3 messages. And what we want to do, we want to hook execution of message box. So let's take a look at the hooking DLL. And this DLL is also pretty simple. Basically, Detours is really simple to use. So let's start with DLL main. So when our DLL gets loaded, it will call hookem function, and when it gets unloaded, it will call unhookem, okay? So what we need for hooking, as I said, we want to target message box, okay? So we need to create a copy of the original message box address, all right? And we also need to create a function which will take over the execution of message box. So I call that hooked message box, okay? So this is our detour function from the documentation. And how the hooking is set. So hookem function is really like straightforward. So any hooking in Detours is done using transactions. So when you want to set a hook, you need to create a new transaction and we start with this detour transaction begin function, and transaction is committed with that call, all right? And setting hook is just calling a detour attach function where you specify the address of the function you want to hook, and the address of the function which will take over the execution of the hooked function. Okay, so in our case, hooked message box. You should also make sure to include detour update thread function. And what this function does, it enlists all the threads that this hook will be applied to, okay? So in other words, this function makes sure that any threads listed here will have a consistent code, okay? And to unhook, you also create a transaction, and the only difference is you just need to call detour detach function, okay, with the same parameters. And this is basically everything. Now our hooked message box function will just print some message on the screen, okay, and that's it. So let's compile them. And let's run hook me. So normally this application works like this. Okay, nothing fancy. So now let's inject our hooking DLL using process hacker. So we inject DLL, we point to our hooking DLL, and now we get the message that the hook has been set, and this message comes from here. Okay, so let's hit OK, and the other two message boxes didn't appear because the message box function has been hooked, right, with our hook me function, which prints this message. All right, so let's rerun it, and let's see under debugger what is actually happening. So let's start the debugger attached to hook me. Let's run it. And before we load the DLL, let's take a look at message box code, which lives in user 32 DLL. Message box. So this is the original message box code. Okay. Now take a look at these first instructions. Now we inject a DLL, and excuse me, and let's reanalyze. And now we see a jump. Okay, so these instructions has been overwritten by the jump instruction from the detours, and the original instructions were copied somewhere else in the memory, and detours make sure that everything is stable. So let's run it, and actually that was actually expected. So yeah, I think you get the idea. Okay, so what we can actually do with this. So our hooking function actually doesn't do much, right? So let me show you how you can actually play with the original message box. So let's say that we want to print, we just want to have some debugging information printed somewhere. So in our case it's on console, but you can print messages to files, for example. And we still want to call the original code, so we can do that like this. So we need to pass all the original parameters to the original message box, okay, and see what happens now. So we can compile that. We run hook me. Let's attach with a debugger. Let's run it so that we can inject our hook me DLL. Now if we go to user 32 and message box, we see the jump, so the hook is already in place. And now let's set the breakpoint here. So F2, run, and hit OK. So execution has been redirected. So if we go back to here, so we went from here, and now the second message box was called, and our breakpoint has been hit. Okay, so let's step into. So this is the code introduced by the Detours. Okay, again, step into, and now we see we are in our detour function. So we are now in here. Okay, we will print something out, and then we will call the original message box. So let's step into several times, and you can see here the message which will be printed out. Okay, here let's step over. We don't need to step into this function, and we see the message, right? So let's go further, and now we should be calling the original message box, but take a closer look how it actually executes. So let's step into, and we landed in this place, and these are the original bytes copied by Detours from the original message box, right? So let's go there, and let's hit it again, and we land in message box. Okay, but on the instruction, you know, after all these instructions which were overwritten by jump. Okay, and now we continue execution, and let's just run that, and our second message box pops up. Okay, this is the third execution, so let's run it again, and the third message pops up. Okay, so this is exactly how Detours work internally. So you have seen the trampoline and the instructions which were copied out. Now let's make it a little bit more like funky. So let's say that we want to only do something else on the second message. Okay, so let's copy that, and let's say that we will call original message box, but if string compare this parameter, so LP text is equal to second message. Okay, so if it equals 0, then we will call the original message box, but we will change the message. So let's say you lose, and let's change the caption to troll. Okay, so only on a second message the second message box should pop up. Okay, so let's save that and recompile. run hook me, and now we don't need to attach the debugger. We'll just inject that and see what happens. So message box is hooked. Okay, let's see. Okay, now our if statement was true, so the message box original message box was called, but we changed the parameters, right? So, and if we hit OK, nothing else happens, because that's what we have implemented in our hooking message box function. So I hope you start seeing, the potential of API hooking, and Detours is really super easy to use and really powerful hooking framework. Another method of hooking is to hook import address table. Okay, so earlier we were playing with inline hooking, so we were trying to intercept the execution flow of the program by overriding binary code in memory. With import address table hooking, this is not the case. We are changing the addresses of imported functions in IAT. Okay, so quick reminder or refresher, let me show you what I'm talking about. So let's hook to Notepad. Let's go to text section, and let's get rid of that. And let's say we want to go to there. So here it is, the import address table. Okay, so instead of patching the code in line, we want to change one of the functions import address table. All right, so let's see the code. And again, we will be targeting our example simple application, and let's take a look at how we can do import address table hooking. So again, we are targeting message box. So this is pretty much the same as with Detours. Our hooked message box function looks pretty much the same. We don't do any conditionals. We will just print some message on a console and then redirect it to the original message box. In DLL main, we will only take care of setting the hooks. And so let's take a look at the hookem function. So what we do, so if you recall from the first chapter, we were talking about PE format, and we were going through all the structures there and parsing them and extracting information we were interested in. Okay, to get to import address table, we were actually jumping through these headers, but there is an Win32 API call called image directory entry to data ex, and this function allows you to easily get to specific data directory in the PE file. So here we define that we want to get straight to import table. Okay, so with this call, you don't need to parse all the PE headers. So we get that address, and then in a loop we are looking for specific module, specific DLL. Okay, we want to target message box, which is implemented in user32.dll. So in this loop we are looking for that and for that library, and if it's found, then we do a simple trick. Normally what we would do, we would go to import lookup table, and then we will parse that lookup table searching for the name of the DLL, and then translate this RVA, this address from there. We can do this a little bit simpler. Let me fire up quickly bbear again, and let's take a look at. Oh, we can actually, yeah, we can go to System32 and Notepad. I just want to show you what I'm talking about. So we were in normally we would go through original func, all these values, and trying to extract the name of the function, okay, and then if we find the right one, then we will change the address pointed by this value. And in our code we do something a little bit smarter. So we take the original function address using just GetProcAddress function, okay? And then instead of going through import lookup table through the original func, we jump straight to the import address table, because we already know the address of the function we want to hook. All right, so that's the slight, I would say, slight optimization for how to do it. So this is exactly what this while loop does. It takes the function address and compares that with the one we extracted from here, and if it's the right one, then we just adjust the protection level on the memory of where this value is stored. We override that address with our address of our hooking function, and we restore the protection level on the memory back to the original. Okay, and that's basically everything we need to do at this point. So let's try to compile the guy. And see if it works. So our target is running. Now let's inject so our function, what does it prints the message, and original box is with changed parameters is called. Okay, so we have you lose with the first message, you lose the second message, and so yeah, it worked, right? Now we can try to, let's try to run the same. We can unload that and close that. Let's try to do this under debugger. Okay, so let's run it again. Let's attach it. And let's go to our, okay, so message box is here. So let's, so this is the address of the message box before the hook. Okay, so now let's hook it. And and the address has changed. Okay, and now it points to our, yep, it looks like our hook message box hooking function. So if we run it, yep, exactly. So that's another method of hooking. Import address table is a good target for hooks. In API hooking, you can also implement your own inline patching in your code without using any external hooking library or framework. So let's take a look at how it can be done. So again, the HookMe program is the same. We are still targeting message box. And now our code looks a little bit differently, but not much. So DLL main is pretty much the same. Our hooking message box is the same. We still need to preserve the original address of message box function. The only difference is hookem function. So at the beginning we preserve the address with getProcAddress of message box. Then we make a copy of original few bytes from the beginning of the function, and then we create our patch. Okay, and I will hold with the explanation of this here because it probably would take too much time, and instead I will show you how it works under the debugger. And the only thing it does is basically patch contains a jump instruction to our hooking function, like the hooked message box. All right, and this patch is being applied to the beginning of the original message box, actually to the function inline in the memory. All right, so let's do this. Let's compile and test it out. So let's start our program. Let's open up debugger. Attach to HookMe. Let's let it run. And so let's first take a look at message box. All right, so this is before patches. So let's inject our DLL. And by the way, the only reason I'm using Process Hacker to inject DLL is just pure convenience. You already know how to inject DLLs and shellcodes into processes, so there is no point to to implement that injector again. Okay. So now our code should look differently, and it is. And let's set up the breakpoint here. So we run it, and our function is just printing message. So let's see this. And where is this? Here. So okay, we hit our jump, our inline hook, And now if you so what this jump does, it will jump to an address which is stored just after the jump instruction. So don't look at these instructions, because the debugger tries to translate these bytes to specific mnemonics and instructions, but what I'm doing here, I'm just mixing the code which is here, this jump, with data which is here, and we can actually let me show you the code again. So the patch works like this. First 6 bytes is a jump instruction, and jump instruction telling that jump to the next instruction after the jump, okay? And after the jump, I store the address, so 8 bytes of the address of our hooking function. Okay, this one I store it here, okay, using memcopy. So we can actually see that a little bit more clearly in the dump. So let me so we have FF25000000. Okay, so we have this is a jump instruction, and then we have it is followed by the address. And how do we know that this is the right address? Because I've implemented printf here, which will print out the address of the message box function. So this message box function address is here: 7F000 7F F8 24 EA 1130, right? So if we step into, we jump to our hooking function, right? So we jump here, and we just do the printf. So we can even set the breakpoint here. Let's run it, and you can see from the parameters that it's going to print the message. So let's step over this call, and exactly what this happened. Okay. And the second breakpoint was hit on the hook, because the second message box has been intercepted. So let's run it again, and the program exits. So this is how you can use the inline patching by hand. Okay. Under this address, there are other options. Instead of using jump and followed by the address, the limitation of this technique, like the patching, creating the patch by hand, is that you don't have that flexibility in your code like when you use external hooking library. And what do I mean by that? I mean by that it is not very easy now to call the original function with original parameters. You need to implement your trampoline function, okay, and make sure that everything is aligned. The context of executing thread is in good state. This is what you get from when you use external hooking library, okay? But if you still want to do that, what we can do, we can actually, if we want to call original function, we can restore the original bytes before the call, and then after original call returns, we set the hook again. Okay, so we can do that, and sort of we should achieve the same goal. So let's attach, and not attach, but inject our DLL there. And now our hooking function should work like original message box, but with one difference, that it will print the additional message on the console. All right. So second message has popped up, but we get the message on the console, and as you can see, the hook has been reestablished. Third message, and we're out. Okay. So let's think about where you can use that. What kind of situation? Okay. So let's say that our function we want to target is not like a simple message box, but a function which checks if a current user has admin rights. All right, let's have that kind of hypothetical situation. So our hooked message box is actually checking if the user is admin or not. So let's say you want to intercept that call, and that this function will only return that you are admin and no one else. All right. So how we can do that? So let's say, since we are targeting everyone, so we need to restore the original bytes and hook every time our function gets called. But let's put let's say that the situation is let me open up this guy as well, and this says Rinzo. Okay, so if our text is Rinzo, then admin access granted. Otherwise, you're just a user. And of course, this code doesn't make sense because it doesn't check any privileges or anything like that. But I just want to make you just show you the example of how you can use hooking to achieve something more than just printing messages on the console. Okay. So let's compile it again, and we have an error. So let's run it again. Hook me. Okay, so we have our first message, and we need to inject to set up our hook. Okay. And now, since the second message, so to speak, the second user was us, then we are granted our function, hooked function, is saying no, yes, this user is an admin. Okay, and The third one is just a user. Okay. So this concludes our API hooking chapter. Sometimes there might be situations when your payload gets executed many times concurrently. And for example, when you set a DLL hijacking persistence and your hijacking DLL gets loaded into multiple processes, okay? Although it's a good thing to have more than one session to a machine, but on the other hand, having too many is also a bad idea because it may create, confusion and bring some chaos and even endanger your operation due to generating too many unnecessary artifacts on the system and network, okay? So it's wise to have some level of control over how many payloads run on the same machine at the same time. And this control is usually achieved by a use of some kind of shared object whose existence means that the payload is already in the memory and all new payloads should back out and cease their execution. The control object could be anything, a file on disk or a key in a registry, but Windows provides many mechanisms dedicated to synchronizing processes and threads in the system. These are mutants, also known as mutexes, semaphores, and events. Even name pipes can be used to signal the payload execution in memory, okay? So let's take a look at how you can use these mechanisms in your project. So in implant.cpp is basically the standard implant template. So we decrypt our payload and try to run it with one small addition, which is this check. And this function is actually trying to figure out if there is any mutex in this particular case, but you can change the control object here. And if it checks if this object is already in the system, and if yes, it means there is another payload running. And in this case, the condition will exit the process. Otherwise, payload will get executed, all right? So let's take a look at the implementation of that function. It is really simple. It supports 4 types of control objects, mutexes, events, semaphores, and named pipes. So it works like this. The first payload which is executing will try to create a mutex, okay, with calling this function, and if it succeeds, and so there is no other mutex of the same name, which is here a global object, then it will return false, all right, which is a default value. Otherwise, if there is such control object in the memory, it means there is something else running, so we will return true, okay? And this is basically the whole logic. So let's try to compile that. And see how it works. So we run first implant. Okay, payload is running. So let's open up another window and try to run the another instance of implant. And this failed to run because of the mutex existing, and we can check that here with Process Explorer. Sync me as the name of our mutex is sync me. So if you try to find it, we have that in this implant, right, running. We can check that to verify. The PID is 1800, right? So, and now if we exit, the control object is gone. So this implant will be able to run the payload. All right. Now, if you, of course, if you want to use any other control object like pipe, you just change that here. Of course, in your project, you don't have to use the whole function. You can just extract one control object, so one condition, like for example event, and get rid of the rest of the code. All right. So this is how you can control your payloads executing multiple times. Now it's time to combine discussed techniques into one practical example. Our target for this project will be VeraCrypt, a popular disk encryption software, and the goal is to be able to steal the password to an encrypted volume without a use of keylogger, okay? You know, a keylogger is always a good option for gathering information and even escalating privileges, but it has one major drawback, which is it produces a lot of junk content, which forces the operator to sift through a lot of unimportant information, okay? From our perspective, we want to get our hands on an encrypted volume file only, so we need a sort of surgical attack to capture a password for that volume, and this is a great use case for API hooking, all right? So for this goal, we will utilize code injection with a payload written in C, compiled into a DLL, and then reformatted into a reflective DLL. We will also need to migrate from a 32-bit process to a 64-bit process and then perform API hooking. So let's see how this would look like. We need to develop 3 payloads, each having a specific task. VCpersist will be an ordinary exe behaving as a container for the other 2 payloads, and it will be executed at user's logon. Here you can use whatever persistence method you want, but we will just use the most basic one, which is startup folder. But of course, there are other, like, more stealthy ways to persist, and all of them are discussed in our dedicated Windows persistence course. So our VCpersist will mimic a VeraCrypt helper binary, whatever it means, all right? And it will inject VC migrate payload into OneDrive process. And why OneDrive? Well, there are a couple of reasons, okay? First, it's a 32-bit binary, so it's a good playground for testing our migration between 32 and 64-bit processes. Second, it starts at user's logon, so theoretically you don't have to be worried about if the process is in memory or not. But of course, in a real situation, we would need to implement more robust checks, okay? And the third reason, and I won't say is, but would be, that OneDrive is a process which talks to the internet, so it's a perfect hideout for your C2 payload communicating with your control channel if we were using any, all right? We aren't, but from the OPSEC perspective, it's a good exercise for a red teamer to have a good candidate for stealthy C2 in your next threat simulation, all right? So after we jump into OneDrive, our VC migrate payload will start to monitor if user executed VeraCrypt, and if so, it will extract VCsniff and inject it into VeraCrypt process. And then VCsniff will set hooks on interesting API calls, allowing it to capture password and save it into a file on disk, which then, of course, can be extracted from the machine, right? All right, guys, let's do this. All right, so let's target VeraCrypt. So we can start with our target. And we can also pin this into taskbar. All right, so our target volume file is this db, okay, this file. And we want to know what is the real password here, okay? I won't tell you that password now, and you won't find that in the course materials. But after we develop our, all our 3 payloads and make them to work, you will eventually see the password in the log file from the sniffer, all right? So for the testing, we will create a new volume, all right? And let's do this now. So standard VeraCrypt volume, that's all right. Select file. Let's put it on a C drive. Test db. Okay. And that's okay. It can be 10 meg. That should be enough. Let's set some password. I use some test password. So let's test mode drive. Test mode drive. It's good to select something unique here so that we will need that string when we will be looking for the API to hook. Okay, so if you select like password, you might get too many false positive. Okay, and a warning: short password. No, yes. Let's continue now. Some randomization, so let's move it a little bit here and there. Okay, format. And we have our volume. So let's set it up on a G drive. Let's see if it works. Test mode drive. And we should have another disk. Oh, refresh. Yes. All right. Okay, so we can dismount that. And now we need to figure out what API call in VeraCrypt process is used to get the password from the user. Okay, so which call gets that string? All right, we could use a debugger for that and go through step by step through the code, but there is a better option. On a C drive, in tools folder, there is a application called API Monitor. So let's run it. And this software allows you to monitor API calls in a specific process. So it basically hooks a lot of calls you select, and then logs them into this application, and you can store that information in a file. All right. So it has several filters. So you can, here in this pane, you select API filter. So you actually say what kind of API calls you are interested in to be monitored. Okay. This pane gives you, it's a display API filter. So you can select which specific API calls you want to look at. Okay, so in this window you will see the API calls which got caught by API Monitor. Okay, and then you can select display filter to filter only those which are interesting for you. All right, and there is also the ability, if there is an external DLL that is not included in by default on Windows, you can add that external DLL and allow API Monitor to intercept the calls from that library. All right. Now it's a question which API calls we should be monitor. Okay. And this is a very valid question. The more filters you enable, the whole process gets more tedious. All right. So it's good to know where to at least how to narrow down the area to focus on. Okay. And in our case, my guess would be Windows UI development. So these calls. Okay. But also the good candidate could be AT native. So this one contains all functions from anti-DLL. Okay, so for the objects, these anti-close, anti-duplicate object, for I don't know, sections, open section, create section, etc. Right. Let's set up the Windows UI and see what happens. I don't know if it's the case, but let's find out. All right. So our process is started. So let's start to monitor it. So right click and start monitoring. Okay, and now you see something is happening. So we start to see the logs coming in. So let's mount our test database. So test mode drive. Wrong password, this one. All right. Okay. Okay, it has finished. So now we can stop monitoring. And now let's search through the string of our test mode drive password. Okay, so it found one and there is no other. So that's a pretty good hit. So what happened here, we see a call to white chart to multi-byte function. And you can see details on that function. So it has 8 parameters with names, code page, these ones, and here we can see our password. Okay, so it's a good thing. I mean, we can even see our password twice, which is weird. Okay. So let's go to the Windows MSDN documentation to see what this function does. Okay, so white chart to multi-byte function declared in string API set header maps UTF white character string to a new character string. The new character string is not necessarily the multi-byte character set. Caution, use function incorrectly can compromise the security of your application. Calling this function can easily cause a buffer overrun because of the size of the buffer equals oh, interesting. I don't think we will need that. All right, let's see the syntax. So we have 8 parameters. Okay, and from the call we know that in the third and fifth we saw our password. All right, so let's investigate these a little bit more. So the first one is code page to use in performing the conversion parameter value of any instance. All right, so these settings possible flags indicating the conversion type can specify the combination of the following values. Okay, so composite check, whatever, invalid chars, no best fit chars. Okay, some flags, whatever. Now third one, white char string, pointer to a Unicode string to convert. Okay, the next one is size in characters of the string indicated by this. Okay, so this one is the size of this one, of this string. Okay, multi-byte string, a pointer to a buffer that receives the converted string. Okay. And multi-byte size in bytes of the buffer indicated. Okay, so this function looks like it works like this. It takes the string from that parameter of that size, converts that into multi-byte string, and saves the result into this buffer of that size. All right. Oh, pretty straightforward. Anything else? Default char pointer to a character to use in if a character cannot be represented. Sets this null if the application whatever. Pointer to a value. Okay. Doesn't think. I don't think it matters. Return value. If successful, returns the number of bytes written to the buffer. If the function returns 0. If it does not succeed. All right. So the last thing we need to check. So it's implemented in kernel 32 DLL, and we can include Windows header for that. Okay, so I think we have everything we need to start implementing our hooking function, our VCsniff, and of course, if you do the production type of code, you should read all this in detail, and because it might help you, some tidbits might be helpful to stabilize your code. Okay, so let's jump back to the VM. All right, so let's save that. We don't need everything, and so let's save this, and let's select all and copy all this just in case we need more details. All right, and we can actually close that. Okay, so we need, so let's think about it. So our VCsniff has to hook into this, the function we have found. And so we need a hooking template, and let's use Detours. So let's copy this guy, and actually let's create a new folder. Let's call it combo. Let's paste and rename it to VCsniff. Okay. This won't be hook me, it's not needed. Let's call it VCsniff. And let's check this. So we don't need to compile this, and VCsniff will produce VCsniff DLL. Okay, let's save that. And here we can copy in this process, this function declaration, okay, from MSDN. Okay, so let's open up VCsniff. All right. So we are targeting another application, another function. So let's copy this. Let's say not this one. Not this one. Okay. The next one is so it will be actually, let's copy the whole thing. let's call it Win API. It's a pointer. Actually, don't need that. Let's copy this one, equals our target function. All right. Now our, it's not hooked function, my message box, it's hooked white car multi-byte. It will be stored here. So let's copy this into this. Save that, and not the original pointer to message box, but to our white chart to multi-byte function. Okay. Now, so let's see. It gets loaded. Hookem gets called, and we set our hook, which does this. So we know from the documentation it gets the string here, and it is converted here. So let's call that function in our let's take this one in our hooking function. So let's get rid of this. We call pointer. Let's get rid of these. Types needs to be removed. Okay. So now our function will just print that, and but we cannot return this one. We need to take, and it's int, so we need an int return. We get the return value, and we will return that on exit. All right. So we can theoretically test that. But instead of printf, we need something else, since this is the DLL running in the remote process. So there will be no console attached. So we can use a function called output debug string a, and this function just prints the we can see the messages printed in the debugger view program. Okay, so let's use that instead of printfs. We have our printfs here. Anywhere else? No. Okay, so let's save that. And it doesn't take any parameters, so we need to get rid of these. Okay. If we want to pass the parameter, we need a buffer. So let's create one buffer, let's say 50 characters long, and let's use as printf with a buffer data equals a string, and actually this, so it was 1, 2, 3. Oh, this is the bad one. Right, we need these. Okay, so we need to fix these parameters as well. So instead of this, we have this. Right. These were just parameters for message box, right? So we need. Okay, and the data comes from. So input string comes from here, and it is converted here. So let's copy this, and let's. So what sprintf does, it will store the result of that mapping. So the value of the string gets mapped to this string, and the resulting like combination lands in a buffer. All right. So that then we can just print it here. So let's printf buffer. Let's see if it works. And then we call it, and I think it looks good to me. Let's try it out. So we need to go to MDI 07, compile. Let's see if, all right, we have an error 25 line. Okay. How about now? Something's wrong. Oh, okay, here. All right. Anything else? Nope. Looks good. All right, let's see. So we need a debug view. Debug view is on C drive in tools. It's a tool from sysinternals. So debug view. Where are you? Here. All right. So let's start it up. And let's dismount it. Now we can inject that using process hacker. Where is it? Here. So inject DLL. Let's go to our proof of concept. Okay, okay, it has been hooked. Cool. Let's try to mount. So test mode drive. Okay. And we didn't get any data. Let's see why. Oh, of course, because we have we did the mapping before calling the original whitechar to multibyte function. Okay, so we need to do this after. Okay. Let's do this. Let's compile it again. And cannot close file. And the reason is because this file is in our target process. It is loaded here. So we need to unload it first. Yep, it has been removed. And now we should be able to compile. Yep. Okay, so let's dismount that. and let's load it again. All right, it has been loaded, so let's try it again. Second time. Test mode drive, okay. And we have our password. Very cool. All right, so we have a working proof of concept. That's pretty neat. So now we need to pass this data into, store this data in on a disk, right? So we need, let's say this call original function and store captured data in a file. All right, so for the file we need a handle, age file. All right, and we will use create file. So we need to open the file first. It returns a file, right? And first parameter is a path. Is a path to a file. So let's say c RDO data.txt. Then we use we want to have it read write, and that we can append the data. So let's use file append data. Yeah, we can share it for reading. This parameter is not interesting. So open always. Open always means that it will either create a new file if it doesn't exist, or open the existing one. And file attribute can be set to normal. And the last one is not important. Okay. Now we need to be sure that everything is okay. So let's check if the file handle is valid. So it was invalid handle value, and if it's not, let's debug. Let's say error with log file. All right, let's use this. And now we need to write our data into the file. So we write file into our file, and actually we should it should actually, if it's not valid, so we return ret. Oh, we don't need that. Let's do this another way. Else read file, and the second is buffer, so where we stored our data, we need a length of that buffer, and there's a size of, so number of bytes written, so there's a D word for that, num bytes. So read file writes the value of how many bytes has been written, and stores that in this variable. All right, and the last one is not important, and we close handle h file. All right, let's save that. And let's try to compile that. Make sure if the, oh, it's still there, so we have to unload that before we compile. Now we compile. And we have error. Cannot convert argument 4 from dword to pointer to dword. Oh, this one. We need to pass the address of the variable, not the variable itself. Let's try it now. Yep, that works. All right. So let's load it again. Let's dismount. Load the guy. And see what happens if so. Test mode drive. Okay. Error with a log file. Okay. So let's go to, so the file was not created. So let's see, append data share. Oh, double backslash. This should do the trick. So we need to recompile. So again, unload. Yes, I'm sure. Let's clean this and recompile. Right? Yep. And load it again. And let's mount it. Test mode drive. Okay. All right, no error. And we have our data. Perfect. Let's try to dismount and mount it again to see if it gets overwritten or not. All right. Okay, it gets appended. Very cool. So I think we are almost good with that. We should actually stop printing any debug information there, right? Let's leave it this one, but as we want to be a little bit more stealthy than usual. So let's recompile again to make sure. All right. And let's load it. Okay, so no messages in there. Let's mount it again. Test mode drive. Okay. Okay, it got mounted. Okay, we have the third entry. All right. So let's check if what happens if I put the wrong password. Let's say trollolo. Okay. What happens if it crashes or not? Well, it needs to think. It takes a while. Interesting. It's it takes a lot of time. It should be a simple check. So let's see what happens. Okay, operation failed due to okay, maybe it checks all these authentication methods. I don't know. It's weird. So let's migrate it again. Let's do some more testing. Mode drive. So let's put the right password. Okay. Yeah, it got logged. And so let's mount another file. Let's say, well, let's unmount that. Let's check something else. DB. Let's mount that like Trollo2. Okay, it seems the same behavior. Or not. Maybe it crashes now. Yes, this is basically the testing period. So I want to make sure that at least it is decently stable. Usually you would need more time for testing, so I won't do that here. But let's see if it breaks or not. But at this point, I think okay, so it failed. All right. It failed for some reason. Okay. So at this point, I think our proof of concept is pretty solid. As I said, normally we would need much more time for testing and make it more robust and predictable. But yeah, as for the VCsniff, I think we are good, and now we can move on to the next project, which is VC Migrate, and we will be migrating from OneDrive, which is 32-bit, to VeraCrypt. Okay, so let's do that in our next project. All right, so the last piece is VCpersist. So let's go to so we need that. Oh, let's check if it exports VC migrate DLL exports. Yeah, it exports Go. So we can okay, take that and oh, we need first so let's think. Okay, so we need a persistent binary which should be executable, and it will inject the first payload. The VC migrate will be injected into OneDrive. So we need something from injections folder. Let's take the classic variations one. Why not? So VC persist. All right, and from migrate we need to take a DLL, which then will be converted to reflective DLL. Okay, so we use Python again, SRDI, Python, not PowerShell, Python, convert, function name was Go, and VC migrate is the name of the DLL. Okay, and we don't have a script here, but the script is in VC migrate AES vcbin and out.txt. All right. So let's call it VCpersist. Let's open up this one and this one. So this would be in our VC migrate shellcode, which is 32-bit, right? So a key, copy, okay, let's save that. Now this file is heavy. It's almost a quarter of megabyte. So, but that's obvious because we embedded another DLL inside, right? All right. So what do we have here? We have decrypt, find target, classic injection. Yeah, let's use inject 2. Which we will be using this one. Why not? And our main, we are targeting OneDrive, which is this one. So OneDrive. Let's payload. Yep, I think that should be it. Let's just not this one. Let's just check. And we can get rid of this. Okay, this doesn't work. It doesn't running. It isn't running, and let's take a look at the compile. No. So let's call it VC, how was it, helper, and let's leave it as console for now. Yeah, this looks good. Yeah, let's compile this. Now it's 64-bit, so let's go to our persist. Let's compile this. And OneDrive is inside, VeraCrypt is not there. Okay, let's run it. So VC helper 6660, not this one. Yeah, it is correct. Let's see the memory. So we have, it looks like our DLL. There's something else. Oh, that's a reflective DLL, ReflectiveLoader. Maybe, who knows? Whatever. Let's run VeraCrypt and see if it gets injected. So test mode drive. Yep, it's correct. All right, and what about here? And the file is 432. Yep, this is working. Ladies and gentlemen, we have everything set up, almost everything, but our persistence, our chain of injections and migrations and hooking seems to work. So the last piece is to actually test that out in the startup folder. So let's implant it. Where is our, let's remove that. And let's take our helper, copy it, and let's go to app data, which is this folder, and we go to Microsoft, Windows, Start menu, Programs, and Startup. Right? Startup. Okay. Paste that. And we can, yeah, let's restart the machine. No, I think not. We need to change the console to, so the application doesn't pop up the black window, the console window at startup. So our VC helper is not visible at logon time. So let's make it Windows. And here we need not main but winmain, which I don't remember the definition of that, how to call that. Let's check our what was it here? No imports, maybe. Let's check it out. Do we have that here? Yes, we do. Copy, and now we can recompile it again. In the meantime, we can go to here. So Z drive MDI 07 VCpersist, compile. App data, Microsoft, Windows, start menu, startup, and it's good. So we copy this guy, copy here, yes, replace. Now this should work. Right, so let's restart the machine and see what happens. So we log in. All right, and we can start VeraCrypt. And now instead of this, we will try to mount the real target. Let's see if F5. So we have a G drive with secrets. All right. So let's go to, and voila. This is the password for our target volume, encrypted volume. All right. So mission accomplished. So I don't know how much time we spend on that. Probably less than 2 hours. And normally you would use much more time, you know, to polish the code, to make it more stable, to set some conditions, and, you know, make sure that everything works works correctly, nothing breaks, and the user is not aware that that kind of sneaky thing is happening in the background. All right. So, yep, we did it. Let's summarize what we have covered during this course. We went through P headers in detail, how to parse them, how to extract information from export and import tables, and also what is process environment block and how it can be used to get information about loaded modules in the memory of the process. Then we looked into custom implementation of GetProcAddress and GetModuleHandle functions, which eventually led to creating a binary without import table. We also discussed few variations of code injection, including ways to execute payload remotely, as well as how to deliver the payload to a target process. Now you also know what is Windows on Windows subsystem and how to use Heaven's Gate to migrate from 32-bit to 64-bit process. Then we covered reflective DLLs in detail, walking through the original code of Stephen Fewer's ReflectiveLoader and playing with its derivative called Shellcode RDI. The last modules talked about API hooking, how to use either complete hooking libraries like Detours, or do it manually by inline patching and import address table hooks. In the final project, we successfully employed these techniques to target a real application to covertly steal password for an encrypted volume. So what are the next steps you can take from here? Well, I would say that with understanding the topics like P headers, reflective DLL injections, with migrations and API hooking, now you possess moderately advanced set of techniques you can use during your penetration testing and red teaming exercises. These capabilities should give you enough flexibility to challenge any blue team you work with and, to some extent against, okay? On the other hand, if you are a blue teamer, knowledge about inner workings of methods used by red teams and real threat actors should enhance your ability to detect and hopefully stop the attack, all right? So the next step I would take from here would be to employ these techniques in my daily work, gain more experience with, different platforms, different applications and environments, because you cannot substitute real hard work, making mistakes, troubleshooting with any course, any book, any presentation, any talk on the conference, all right? Experience is king, and it just has to be earned, okay? Thank you very much for purchasing this course. It was great pleasure again to share my experience with you, and I hope you have learned a lot and that this knowledge will push you further in your ethical hacker career. My name is Rinzo, and that was Red Team Operator Module Development Intermediate course. Cheers, and see you next time!